Pepsi, M&Ms, and Skittles all depend on one thing people never notice. Before they become the product, they are built through layers of syrup and timing that have to come out exactly the same every time. In this documentary, we dive into how 3 completely different treats are produced and finished before they become instantly recognizable. Pepsi cans lock shut under a double seaming head, while the cola inside is still cold, pressurized, and fizzing against the lid. A filled aluminum can enters the seamer through a star wheel. The can body is open at the top, and the carbonated Pepsi sits just below the rim with a controlled headspace above it. A lid drops onto the can flange. The seaming chuck holds it in place. Rollers move in with precise pressure, curling the lid edge and can flange together into a tight double seam. The first roller forms the metal. The second roller compresses it. The seam becomes a folded mechanical lock that holds carbonation without glue. The can leaves the seamer sealed, rigid, and ready for inspection. Inside, dissolved carbon dioxide remains trapped under pressure. Before the can reaches the seamer, it is filled in a rotary pressure filler. Empty cans move into the filler after rinsing. They are spaced by star wheels and carried around a circular filling bowl. Each can rises under a valve. The valve controls liquid flow, so the carbonated drink enters quickly without excessive foam. The Pepsi stream is cold at this point. Cold liquid holds carbon dioxide more efficiently and behaves more calmly during filling. The dark cola enters the can in a controlled flow. The level rises with fine bubbles moving upward through the liquid. When the programmed fill height is reached, the valve closes and the can moves immediately toward the lid feeder. The filler must work with speed and restraint at the same time. Carbonated liquid wants to release gas when pressure changes. The filling valve shapes the flow to reduce splashing. The short transfer from filler to seamer prevents gas loss before closure. The carbonated beverage arrives at the filler through closed stainless steel pipework. The line remains pressurized and smooth. Sharp turns and sudden pressure drops are avoided. The liquid moves from the carbonator to the filling bowl without open exposure. Inside the carbonator, chilled flat Pepsi receives carbon dioxide. The liquid enters through a controlled feed line. Carbon dioxide enters under pressure through diffusers or contact surfaces. The gas breaks into fine bubbles and dissolves into the cola. The system controls pressure, liquid temperature, and gas flow, so every batch reaches the target carbonation level. The beverage is chilled before carbonation. It passes through a plate heat exchanger, where thin stainless steel plates separate the cola from a cold circulating fluid. Heat leaves the beverage rapidly. The liquid exits cold, dense, and ready to absorb gas. Some lines remove dissolved air before carbonation. In a deaeration unit, the flat drink moves under reduced pressure. Tiny air bubbles separate from the liquid and are pulled away. This makes carbonation more consistent and helps the drink hold its sparkle after sealing. The flat Pepsi comes from a blending system. Treated water and concentrated syrup meet at a proportioner. The syrup line is dark, sweet, and strong. The water line is clear and neutral. Flow meters measure both streams, and automatic valves adjust the ratio continuously. As the 2 streams combine, the syrup thins into finished strength cola. The color remains deep brown, but the flavor, sweetness, acidity, and body shift into the final beverage balance. This flat cola moves directly toward chilling, deaeration, and carbonation. The syrup is made in a separate syrup room. Treated water enters a stainless steel mixing tank. Sweetener is added first. It may arrive as liquid sweetener or as sugar dissolved into the water. The tank agitator keeps the base moving, so no dense layer forms at the bottom. When sugar crystals are used, they fall into the water and gradually disappear. The mixture becomes heavier and glossy as the solids dissolve. Recirculation pumps may draw syrup from the bottom and return it near the top, creating a uniform sweet base. The sweet base passes through filtration before flavoring. Fine screens or filters remove undissolved material. Clean syrup protects proportioning valves, pumps, and filling equipment later in the process. Pepsi concentrate then enters through a closed dosing line. Caramel color spreads through the sweet base. Acids and flavor components blend into the liquid. The tank changes from clear syrup into a dark cola concentrate. The agitator turns steadily until the batch is uniform from the surface to the outlet. The finished syrup is much stronger than the drink itself. It is held in a tank with slow agitation. Pumps send it forward only as the proportioner requires it. The syrup flow and treated water flow create the finished cola continuously during production. The treated water begins as incoming plant water. It moves first through particulate filtration to remove suspended solids. It then passes through activated carbon, which reduces unwanted taste and odor. Additional polishing steps create a consistent water base for syrup making and final blending. This water matters because it makes up most of the beverage. Its clarity, taste, and mineral balance must stay steady. Sensors monitor flow, pressure, and treatment performance before the water enters storage tanks. While the liquid side is prepared, containers move through their own system. Aluminum cans arrive empty, lightweight, and open at the top. They are already formed and printed before entering the filling hall. The cans feed from depalletizers into single-file lanes. Air conveyors and guide rails control their movement without crushing the thin walls. Before filling, the cans are rinsed. They invert, receive a blast of filtered air or treated rinse water, drain, and return upright. This removes loose particles from the interior before the cola enters. PET bottles follow another route. They often begin as preforms. A preform is a short, thick plastic tube with a finished threaded neck. The body has not yet been expanded. The preforms enter a heating oven and rotate beneath infrared lamps so the plastic warms evenly. A heated preform enters a blow mold. The mold closes around it. A stretch rod pushes down through the center, pulling the softened plastic lengthwise. Compressed air then expands it outward until it touches the chilled mold walls. The base, shoulders, sidewall, and label panel form at once. The mold opens and the empty bottle exits by its neck ring. Air conveyors carry it forward. Because the bottle is light before filling, air jets can push it along while rails support the neck finish. The bottles pass through rinsing before filling. Each bottle is gripped, inverted, cleaned internally, drained, and returned upright. It then enters a pressure filler similar in purpose to the can filler, but matched to bottle geometry. For plastic bottles, the filling valve seals around the mouth. Pressure is balanced before liquid enters. Pepsi flows into the bottle with controlled turbulence. The fill level rises to the target height, and the valve closes. The filled bottle moves immediately to capping. Caps are sorted in an orienting bowl and sent down chutes to the capping heads. Each cap lands on the bottleneck and tightens to a controlled torque. The tamper band locks below the neck ring as the cap finishes turning. Glass bottles use a heavier container path. They pass through inspection before filling. Cameras and light systems check the mouth, base, sidewall, and interior. After filling, crown caps or threaded closures seal the bottle. The closure must hold carbonation pressure as the beverage warms and moves through packing. Every sealed container enters inspection. Fill level sensors check the liquid amount. Cameras inspect caps, can seams, bottle shapes, crown placement, dents, thread finish, and printed decoration. Any defective unit is removed automatically from the conveyor. Filled containers are often wet on the outside because the beverage is cold. Air knives remove condensation. Thin, high-speed sheets of air strike the cans and bottles from multiple angles. Droplets break away from lids, seams, shoulders, labels, and bases. M&M's pieces gain their hard candy shells through repeated polishing, coloring, and drying cycles inside large rotating pans. The chocolate centers arrive at this stage as small, rounded cores. They are already formed, cooled, and firm enough to tumble without flattening. The centers enter wide coating pans that rotate at a steady angle. As the pan turns, the centers climb up the inner wall, slide back down, and roll over each other in a continuous shifting bed. A sugar syrup is added in very thin amounts. It does not pour in heavily. It enters as a controlled stream or fine spray. The syrup touches the moving centers and spreads across their surfaces. Drying air flows through the pan, removing moisture from that layer. The syrup hardens into a thin shell. The cycle repeats again and again. A small dose of syrup coats the centers. The pieces tumble. Air dries the surface. Another dose follows. Each layer adds thickness. The round centers gradually become slightly larger, smoother, and stronger. This is how the shell is built, not in one thick coat, but in many thin, hardened layers. At first, the shell is plain and pale. Later, color is added to separate batches. Red pieces receive red syrup. Yellow pieces receive yellow syrup. Blue, green, orange, and brown batches move through their own color systems. Each color must remain separate until blending, because the coating pans create one color at a time. The pan speed controls the shape. If the movement is too slow, pieces may stick together or develop flat spots. If it is too fast, they can chip or bounce unevenly. The pan turns just enough to keep the candy rolling smoothly while the coating dries. Drying air is just as important as syrup. If the air is too weak, the pieces stay wet and clump. If it is too aggressive, the surface can roughen or dry before the coating spreads. Air temperature, humidity, and flow rate are balanced so the shell becomes hard, even, and glossy. Before these coating pans receive the centers, the chocolate cores are made in a separate process. Chocolate mass begins with cocoa ingredients, sugar, milk ingredients, cocoa butter, and fats blended into a thick paste. The paste passes through refining rollers that reduce the particle size. Sugar crystals, cocoa particles, and milk solids become fine enough that the finished chocolate feels smooth instead of gritty. The refined chocolate enters conching equipment. Heavy mixing arms work the chocolate under controlled heat. The mass becomes more fluid as fat spreads around the tiny particles. The texture becomes smoother, and the chocolate develops the flow needed for forming centers. The chocolate then moves into tempering. Tempering controls the cocoa butter crystals inside the chocolate. The liquid chocolate is cooled and gently reheated through specific temperature stages. This gives the chocolate the ability to set firm and resist smearing during later coating. To form the centers, tempered chocolate is deposited into small molds or dropped in measured portions onto a cooling surface, depending on the product type. For classic milk chocolate M&Ms, the goal is a small, lentil-shaped center. The chocolate must settle into a rounded disc that is thick in the middle and thinner at the edges. The formed centers pass through cooling tunnels. Cold air removes heat, and the chocolate solidifies. The centers contract slightly as they set. Once firm, they release from molds or separate from the forming surface. They are then screened to remove broken pieces, doubles, or misshapen centers. Some M&M's varieties need a different center. Peanut M&Ms begin with roasted peanuts. The peanuts are cleaned, sized, and roasted until their moisture drops and their texture becomes crisp. After cooling, they are coated with chocolate before shell building begins. Each peanut becomes the center around which chocolate and candy layers are added. Peanut butter centers use a prepared paste. Ground peanuts, sweetener, fat, and stabilizing ingredients are mixed until thick and smooth. The paste is formed into small cores, chilled, and coated with chocolate or candy layers depending on the line. Pretzel or crispy varieties use baked centers that must remain dry and strong before coating. For the classic chocolate type, the cooled chocolate centers are transferred toward the panning room. The centers are loaded into the coating pans by measured batch weight. The pans begin rotating and the first shell building layers are applied. A base syrup layer helps seal the chocolate. This prevents color syrup from interacting directly with the chocolate surface. The early layers also strengthen the center so it can tolerate many more coating cycles. The pieces are repeatedly wetted and dried until the shell reaches the required thickness. The surface becomes harder with each cycle. When enough base shell is built, color coding begins. Colored syrup layers add brightness and identity to the candy. Each batch continues tumbling until the color is even. The pieces must not show pale spots, streaks, or exposed base layers. The rolling action distributes syrup across the top, bottom, and edges of every piece. Because each candy is small and constantly moving, the final shell becomes smooth and rounded. After coloring, the pieces move into polishing. A polishing solution is added in tiny amounts while the candy tumbles. The surface becomes brighter and glossier. Friction between the pieces helps smooth microscopic roughness. The candy changes from matte-colored pellets into shiny finished M&Ms. The polished candies are discharged and cooled. They move through screens that separate out small fragments, oversized clusters, chipped pieces, and dust. The accepted pieces continue by color into holding bins. The white letter is added after the shell is complete. The candies move into a printing system that orients and contacts the pieces quickly. A food-grade white marking material is transferred onto one side of each candy. The printing mechanism must apply the mark without cracking the shell or smearing the surface. Because M&Ms are rounded and small, perfect orientation is difficult. The system uses controlled feeding, vibration, and contact printing to mark the moving pieces at high speed. The printed candies pass through a short drying section, so the letter sets before blending and packaging. Different colors are then blended. Each color stream feeds from its own hopper. Vibrating feeders meter red, yellow, green, blue, orange, and brown pieces into a common conveyor or blending drum. The ratios are controlled so each finished package receives a balanced mix. The blending must be gentle. The shells are hard, but they can still chip if dropped too far or crushed between equipment surfaces. Conveyors, chutes, and drums are shaped to keep the pieces moving smoothly. The mixed candies enter the weighing system. For small bags, a multi-head weigher divides the candy into several weigh buckets. Each bucket holds a small portion. The machine calculates which bucket combination equals the target weight, then releases those portions together. The selected candy drops into the bagging machine. Printed film unwinds from a roll and moves around a forming tube. The film edges meet and seal vertically, creating a tube. The candy falls through the tube into the open package. Horizontal sealing jaws close the bottom of one package and the top of the previous one. The jaws also cut the packages apart. Each bag leaves sealed, filled, and separated from the film web. For larger stand-up pouches, film is formed with gussets that allow the bag to stand. The pouch is filled by weight, sealed at the top, and cooled at the seal area so the closure holds cleanly. Resealable formats receive a zipper strip integrated into the film before the top seal is completed. For small tubes, cartons, or theater boxes, the packaging path changes. Paperboard blanks open into box shapes. Candy is weighed or volumetrically metered into each carton. Flaps fold in sequence and lock or glue shut. The package then moves through inspection and coding. For bulk formats, candies are filled into larger bags or tubs. The filling system uses wider chutes and heavier weighing equipment. The same controls apply correct weight, clean closure, shell protection, and consistent color blend. Every package passes through inspection. Check weighers verify that the amount of candy is within the target range. Metal detectors scan the package. Vision systems check seal quality, print alignment, code presence, bag shape, and carton closure. Coding equipment applies production information to the bag, pouch, carton, or outer case. Inkjet or laser systems print while the package moves on the conveyor. A scanner can confirm that the code is readable. Accepted retail packs move into secondary packing. Bags may be counted and loaded into display cartons. Cartons may be grouped into corrugated cases. A case former opens a flat blank or folded case, seals the bottom, and presents it for loading. Mechanical pushers or pick-and-place systems load the retail packs into the case. The arrangement depends on package shape. Flexible bags need gentle compression. Boxes stack more tightly. Pouches may stand upright or lay flat in rows. Skittles centers are cut from a thick, fruit-flavored candy rope before their colored shells are built around them. The center mass starts as a chewy sugar base. Sugar, glucose syrup, and water are cooked together until the mixture reaches the correct solids level. Heat drives away moisture, and the syrup becomes dense, clear, and heavy. The cooked syrup is not yet a finished candy. It is a hot, elastic base that needs acid, flavor, color preparation, cooling, and forming. The hot candy mass moves onto a cooling table or through a continuous cooling system. As it cools, it becomes thicker and more workable. Acid ingredients and fruit flavor components are added while the mass is still soft enough to fold. The mixing action pulls the flavor through the candy until every section has the same sharp fruit profile. The base must stay pliable. If it cools too far, it becomes difficult to shape. If it stays too warm, it stretches too much and will not cut cleanly. Temperature controls the entire forming stage. The candy mass is worked into a long rope. Rollers and forming wheels pull it forward and reduce its diameter. The rope becomes smooth, rounded, and even. Inside, the candy is dense and chewy. Outside, the surface firms just enough to hold shape. The rope enters a cutting machine. Rotating knives or forming dies divide it into small pillow-shaped centers. Each cut creates a soft pellet with rounded edges. The pieces are still not shiny, hard, or fully colored like finished Skittles. They are chewy cores waiting for shell coating. The cut centers move on to cooling conveyors. Air removes heat and firms the surface. The centers must become strong enough to tumble in coating pans without sticking together or deforming. They remain chewy inside, but the outside develops enough firmness for panning. The centers pass through sizing screens. Pieces that are too small fall away. Oversized pieces and doubles are removed. Correct size centers continue toward the coating area. The sorting step helps the finished candy feel consistent, even though millions of pieces move through the line. The accepted centers enter large rotating coating pans. These pans are wide, smooth, and tilted. As each pan turns, the centers climb the inner wall, then roll back down over one another. This tumbling motion exposes every surface repeatedly. A sugar syrup is prepared separately for shell building. Sugar, glucose syrup, water, color, and other coating ingredients are cooked and held at a controlled temperature. The syrup must flow through spray nozzles, but it must also dry into a hard shell once applied. The first shell layers are usually built gradually. A small amount of syrup is added to the tumbling centers. The syrup spreads across the surface. Drying air flows into the pan and removes moisture. The thin layer hardens. Then another small amount is added. The shell forms through repetition. Spray, tumble, dry. Spray, tumble, dry. Each cycle adds a little thickness. The pieces become stronger and smoother with each pass. The centers stay chewy while the outside begins developing a crisp sugar shell. The pan speed must be carefully controlled. Slow tumbling can cause clumping and flat spots. Fast tumbling can chip the growing shells. The best motion keeps the pieces rolling continuously, with a dry rattling sound as the shell hardens. Drying air is adjusted for temperature and humidity. If the air dries the syrup too slowly, pieces stick together. If it dries too fast, the surface can become rough. The coating layer must spread before it sets, then crystallize evenly. Each flavor color batch is handled separately. Lemon pieces receive yellow coating. Orange pieces receive orange coating. Strawberry, grape, lime, green apple, or other flavors receive their own colors depending on the product version. The fruit center and outer color must match the intended final mix. As the coating builds, the pieces change from soft pellets into bright candy buttons. They become smoother and rounder, but they keep a slight flattened oval shape. The shell grows thick enough to give the first crisp bite before the chewy center begins. After the main color coating is finished, polishing begins. A very small amount of polishing solution is added while the candy continues tumbling. Friction between pieces smooths the surface. The candies become glossier. The shell shifts from dull color to bright shine. The polished Skittles leave the coating pans and move onto cooling and drying conveyors. The shell must stabilize before printing. If the surface remains tacky, the printed mark can smear. If the shell is too brittle or dusty, the print will not transfer cleanly. The pieces pass through screens and air separators. Loose sugar dust, broken fragments, and clusters are removed. The accepted candies move into color-specific holding bins. Each bin holds one finished color and flavor. The white S is applied in a printing stage. Candies feed from hoppers into channels or pockets that position them for contact with printing equipment. A food-grade white marking material transfers onto the shell surface. The equipment touches each candy briefly, leaving the letter without cracking the shell. Printing small rounded candies is difficult because each piece can land at a different angle. The feeding system uses vibration, channels, and controlled flow to improve orientation. Not every motion is forceful. The candy must move fast, but the shell surface must remain intact. After printing, the candies pass through a short drying section. Air sets the printed mark so it does not smear during blending. The pieces now have the full outside appearance: bright shell, glossy surface, and white printed letter. Blending happens after colors are finished and printed. Each color feeds from its own hopper. Vibrating feeders release measured amounts onto a common conveyor or into a blending drum. The system controls the ratio, so the finished bag receives the intended color mix. The blending motion must be gentle. Skittles shells are hard, but they can chip if dropped from high distances or squeezed under heavy pressure. Chutes are curved. Conveyors are controlled. The candy flows like small polished stones without being crushed. The mixed candy moves toward the weighing system. A multi-head weigher handles the irregular flow. Candy feeds into many small buckets. Each bucket holds a partial amount. The machine calculates which combination of buckets equals the target pack weight. The selected buckets open together. Skittles drop into a funnel and enter the bagging machine. The fall is short and guided to prevent cracking or bouncing out of the forming tube. Packaging film unwinds from a roll. The film is printed before it reaches the machine. Registration sensors read marks on the film, so each bag is cut and sealed in the correct place. The film passes over a forming collar and wraps into a vertical tube. A vertical seal closes the back of the tube. Horizontal jaws close the bottom. The weighed candy drops into the open package. The jaws close again above the candy, forming the top seal of one bag and the bottom seal of the next. A knife cuts between seals, releasing a finished bag. The sealed bag contains a controlled amount of mixed color Skittles with enough internal space to move without crushing. The film protects the candy from moisture because humidity can dull the shell and make the surface sticky. Pringles are manufactured as a formed potato and starch dough that is rolled into a thin sheet, stamped into a precise saddle shape. cooked to low moisture for crispness, seasoned, then stacked and packed so every crisp fits the same tube geometry. The entire process is built around the final stack because the product must be dimensionally consistent to nest cleanly. That means thickness, curvature, and shrink must be controlled more tightly than in sliced chips. The line, therefore, treats dough rheology and forming temperature as primary controls, not just cooking time. The last operation before packaging is stacking. After cooking and seasoning, the crisps move into orienting channels that flip them into a single consistent face direction. Orienters rely on the saddle shape to guide each crisp into the correct orientation. Pieces that are too flat, too curled, or warped will not travel correctly and will jam. For that reason, dimensional inspection and curvature control are enforced upstream. Once oriented, crisps enter a stacker that nests them into a column. Stack height is counted or measured by length sensors, so each tube receives a consistent number or mass. The stack is pushed into a tube, and the tube is sealed with a cap and foil or membrane, depending on the packaging design. Packaging is not passive. The tube protects the product from breakage and also provides a controlled headspace environment. The tube seal must be tight because moisture uptake softens the crisp. Barrier materials and sealing parameters are chosen to keep water vapor transmission low. Seasoning is applied immediately after cooking, while the surface still carries enough oil to act as an adhesive. Crisps pass through a rotating drum where fine seasoning powder is dosed by mass flow. Drum speed is tuned so crisps tumble without snapping. Because Pringles are uniform, seasoning distribution can be very consistent if the oil film and residence time are stable. Excess seasoning is controlled because too much loose powder collects at the bottom of the tube and affects consumer perception. Cooking creates both crispness and a stable shape. Unlike sliced chips that float in oil, Pringles are often fried on a conveyor or baked then fried depending on the process variant. The key requirement is that moisture is reduced to a low end point while the crisp is held in its saddle form. If the shape is not held, the sheet will shrink unpredictably and curl. Crisps are carried through hot oil on a belt or between forming elements that maintain curvature. Oil temperature is held tightly because it controls how quickly water leaves and how the surface sets. If oil is too cool, the crisp stays longer, absorbs more oil, and can become heavy. If oil is too hot, the surface sets before the interior dries evenly, leading to blistering or brittle weak spots. Residence time is synchronized with line speed and thickness, so the final moisture endpoint is reached consistently. Oil management remains critical. Crumbs and fines are filtered out because they burn and darken oil, changing heat transfer and flavor. Oil circulation keeps temperature uniform across the fryer width. Consistent oil quality helps maintain consistent color and prevents off notes. After frying, excess surface oil is removed with drains and air knives, so the seasoning step begins with a controlled oil film rather than variable pooling. Before frying, the product is formed mechanically from a dough sheet. The sheet is created from a blended dry base and a controlled water addition. The dry base typically includes potato flakes, potato granules, and starches that set structure. Flour or other binders can be included to tune elasticity. Dry ingredients are screened to remove lumps because lumps create weak spots that tear during sheeting and show as holes in the crisp. Water and any minor liquid ingredients are metered into a mixer where the dry base hydrates and becomes a cohesive dough. Mixing intensity is controlled because too much work develops elasticity that causes snapback and warping when stamped. Too little work leaves dry pockets that crumble and tear. The dough must be plastic enough to roll into a thin sheet without cracking, but not sticky enough to smear on rollers. Dough temperature is controlled because it drives viscosity. Warmer dough becomes softer and can stick to rollers. Colder dough becomes stiff and cracks at the sheet edges. The line aims for a narrow temperature band and uses jacketed mixers or conditioned rooms to keep that band stable. Resting time can be used after mixing to allow moisture to distribute evenly, which improves sheet uniformity. Sheeting is done through roller mills that progressively reduce thickness. The dough passes through a series of gaps rather than one large reduction. This prevents tearing and keeps thickness uniform across the width. Gauge rollers at the end set the final sheet thickness. Thickness control is one of the most important variables because thickness determines final crisp strength and how it nests in a stack. Even small thickness differences change curvature behavior during forming and change cook time in the fryer. The sheet then enters a stamping and forming section. A cutter punches oval blanks from the sheet. Scrap around the ovals is collected and returned to the dough system at controlled ratios. Rework ratio is controlled because repeated rolling changes hydration and can increase fines, affecting dough behavior. The oval blanks are transferred immediately into forming molds that create the saddle geometry. Forming molds are paired surfaces that press the blank into a curved shape. The blank is held in this geometry as it enters the cooking stage or a pre-dry stage. Holding shape during early heating is critical because shrink begins as moisture moves and starch sets. If the blank is not constrained, it shrinks unevenly and warps. Many lines use a pre-dry or bake step before frying. A brief bake removes some moisture and sets the surface so the blank can move into oil with less deformation. Baking also reduces the time in oil, which can help control oil pickup. The bake profile is tuned so it stiffens the shape without fully drying the piece. The piece must still be pliable enough to conform to the mold and avoid cracking. When the molded pieces enter the fryer, they are supported so they do not float and lose curvature. Belts and mold carriers maintain spacing and prevent contact between pieces. As moisture leaves, the structure becomes rigid. The exit condition is a crisp that is dry enough to snap, uniform enough to stack, and strong enough to survive handling. After frying, the pieces are cooled briefly to stabilize the structure before seasoning. Cooling also reduces surface volatility and helps the oil film set. Pieces then enter the seasoning drum. The drum uses gentle tumbling to distribute powder. Seasoning rate is synchronized with product throughput, and drum residence time ensures coverage without overhandling. Following seasoning, pieces are inspected and sorted. Vision systems can detect warped or broken pieces that would jam stackers. Out-of-shape pieces are rejected. This sorting step is important because stacking systems require consistent geometry to nest smoothly. Even a small number of warped pieces can create stack misalignment and tube filling issues. The oriented pieces then enter the stacker. Orientation channels guide each crisp into the same direction. The stacker nests pieces into a column and transfers the column into a tube. Tube filling is synchronized so stacks do not collide and break. Once in the tube, the product is protected from crushing and from moisture ingress. The tube is sealed, coated, and then cased. Doritos are manufactured by turning corn into a cooked masa, converting that masa into thin sheets, cutting the sheets into triangles, frying to a controlled moisture endpoint, then applying seasoning through an oil film so each chip carries a dense, uniform flavor layer without clumping. The process is anchored around seasoning adhesion because Doritos carry far more powder per unit surface than plain chips. That means the chip must leave the fryer with the right surface oil level and the right dryness. Too much oil creates heavy seasoning pockets and greasy mouthfeel. Too little oil produces bald spots and uneven flavor. The factory therefore tunes frying, de-oiling, and seasoning drum conditions as a single linked system rather than independent steps. After frying, There are chips pass through drains and controlled agitation that remove free oil while leaving a thin adhesive film. Vibration and mesh conveyors let oil fall away. Air knives can strip surface oil selectively. The target is a consistent oil film thickness that supports seasoning pickup. From there, the chips enter a seasoning drum where powder is dosed by mass flow. Drum rotation rolls the chips so both sides see powder. The powder blend includes fine salt, acids, dairy solids, spices, and flavor compounds, and it must remain free-flowing to distribute evenly. The drum residence time is long enough for coverage, but short enough to avoid breaking chips into fines. Excess powder is minimized because loose powder settles in bags and contaminates seals. Packaging begins right after seasoning. Chips feed into multi-head weighers that portion weights by combining multiple hopper dumps. Gentle drop paths reduce breakage. Bags are formed from barrier films and are often nitrogen flushed to displace oxygen and create headspace that cushions chips. Seals are made with controlled heat and dwell so the bag closes without leaks. Moisture and oxygen barriers protect crispness and flavor stability over time. All of that downstream performance depends on how the chip was built upstream. Doritos start as corn that is converted into a dough called masa. The primary transformation is cooking corn kernels in an alkaline process. Whole corn is cooked in water containing a controlled amount of alkali. This step changes the kernel structure and helps loosen the hull. It also alters protein and starch behavior so the later dough forms correctly. Cook time and temperature are controlled because overcooking produces a sticky dough that sheets poorly. Undercooking produces a grainy dough that cracks. After cooking, the corn is steeped to complete hydration. Steeping time is controlled so water penetrates the kernel uniformly. The cooked kernels then go through washing to remove loosened hull material and to adjust surface chemistry. Wash intensity is controlled because too much washing can strip solids and change dough behavior. The washed kernels are then ground into masa using stone mills or modern grinders that produce a uniform particle size distribution. Grinding is tuned for sheetability and bite. If the grind is too coarse, the sheet will have weak points and tear during cutting and frying. If too fine, the dough becomes overly cohesive and can shrink unevenly. Water is added during grinding or immediately after to reach a target dough moisture. Moisture is the key variable that determines how easily the masa sheet forms and how it fries. The dough must be plastic enough to roll without cracking, but not so wet that it sticks to rollers and creates thickness variation. Masa mixing follows grinding. Mixing distributes moisture and stabilizes the dough. Resting can be used to let moisture equilibrate, which improves sheet uniformity. Dough temperature is also controlled because warm dough becomes sticky and cold dough cracks at edges. The system uses jacketed equipment or controlled ambient conditions to keep dough in a narrow temperature band. Sheeting converts masa into a continuous thin band. The dough passes through multiple roller gaps that gradually reduce thickness. Gradual reduction prevents tearing and keeps thickness uniform. The final gauge gap sets chip thickness. Thickness drives frying time and final crunch. It also drives how much seasoning can be carried because thicker chips have more structure and surface roughness. The sheet then enters cutting. Rotary cutters punch triangles at high speed. Cutter timing and alignment define triangle shape and minimize scrap. Scrap sheet around triangles is collected and reintroduced into the dough stream in controlled ratios. Rework ratios are limited because repeated rolling changes, hydration, and particle damage, which can increase fines and change sheet strength. Before frying, the triangles are conditioned. Some lines use an oven or pre-dryer to remove a portion of moisture and set surface structure. Pre-drying stabilizes shape and reduces time in oil, which can reduce oil pickup. The pre-dry profile is tuned so the triangle becomes firm enough to handle but still flexible enough not to crack. Frying is the main crispness forming step. Triangles enter hot oil and immediately release steam as surface water flashes. The steam creates pores and drives moisture out. As moisture drops, the structure rigidifies and the chip becomes brittle. Oil temperature is held tightly because it controls the rate of water removal and the degree of browning. Too cool yields oily, flexible chips and inconsistent seasoning adhesion. Too hot yields fragile chips that darken and break. Residence time is controlled by conveyor speed and chip bed depth. Bed depth must be shallow, so every chip sees similar oil contact and heat transfer. Oil circulation maintains uniform temperature across the fryer width and prevents cold spots. Filtration removes fines and crumbs that burn and darken the oil. Oil turnover keeps oil quality stable, so flavor and color remain consistent. After frying, chips pass through a color sorting system on many lines. Optical sensors detect overly dark chips or defective shapes and eject them. Sorting tightens visual consistency in the bag and removes chips that would taste more bitter from heavier browning. The fried chips then go through the de-oiling steps that were set up to support seasoning pickup. The factory treats de-oiling and seasoning as a coupled system. If the seasoning formula changes, the target oil film may change too. Fine powders require less oil to adhere evenly. Larger particle blends may need slightly more oil. The line adjusts drain time, vibration intensity, and air knife settings to land at the correct film. Seasoning powder handling is its own process because Doritos powders are complex blends that must remain free-flowing. Powders are blended in large mixers and screened to break clumps. Moisture control is critical because humidity causes caking. Feeders meter seasoning into the drum at a rate proportional to chip mass flow. The drum is designed to provide enough tumbling for even coating without creating breakage. Interior lifters lift chips and let them fall through a powder cloud, promoting coverage on both sides and edges. After seasoning, the chips are screened lightly to remove loose fines. This reduces dust in the bag and helps maintain seal integrity. Then the chips are weighed and bagged, flushed with gas, and sealed. Case packing stacks bags in a way that reduces crushing forces and keeps headspace intact, because the headspace acts as a cushion. Walker-style crisps are manufactured by engineering a thin potato slice into a dry, brittle matrix with a controlled surface oil film, then locking that texture in with fast packaging that blocks moisture and oxygen. The process is easiest to follow from the fryer exit because the fryer decides the final crunch and the exact oil level that seasoning needs in order to stick. As slices leave hot oil, they are still losing steam through their pores. If they are held too long without draining, oil can continue to migrate into those pores as internal pressure drops. The line therefore moves crisps immediately onto draining conveyors and vibration decks. Vibration shakes off free surface oil, while the crisp is still rigid enough to tolerate movement. Air knives can strip oil from curled edges and from the center dish area. The objective is not a completely dry surface. It is a consistent, thin oil film that supports seasoning and gives the correct mouthfeel. Seasoning is applied while that oil film is still warm and mobile. Crisps enter a rotating drum where seasoning powder is metered by mass flow to match crisp throughput. Drum internals lift and cascade crisps so powder distributes across faces and edges. Drum speed is tuned to roll crisps without grinding them into fines. Too much agitation creates dust that collects in bags and contaminates seals. Too little agitation yields patchy coverage. For lightly salted crisps, the dosing rate is low and distribution must be especially uniform because any local salt cluster is obvious. For flavored crisps, the powder mix is more complex and often includes fine salt, acids, dairy solids, spices, and flavor carriers that need controlled humidity to remain free-flowing. After seasoning, crisps are screened to remove small fragments and fines created in slicing and frying. Removing fines improves bag appearance and reduces dust that can weaken seals. It also helps keep seasoning distribution predictable because fines carry disproportionate seasoning. Packaging is designed to preserve the crisp matrix that was created in the fryer. Multi-head weighers portion weights by combining multiple small hopper dumps. Drop paths are designed to reduce breakage. Bags are formed from barrier film and typically flushed with nitrogen to displace oxygen and create a cushioning headspace. The nitrogen headspace reduces oxidation and protects crisps from crushing. Heat seals close the bag. Seal temperature and dwell time are tuned so seals hold without wrinkles that would leak. Even small leaks allow moisture ingress, which softens crisps by raising water activity and plasticizing the starch matrix. The fryer performance that makes all of this work depends on what happened to the potato slice before it reached oil. Slices must enter the fryer separated with low surface starch and with minimal free water. If slices stick together, they cook unevenly and trap moisture. If surface starch remains, it forms a sticky film that encourages clumping and creates dark specks in oil. If surface water remains, it cools the oil locally and increases oil breakdown. That is why the pre-fry section is built around starch and water removal. Immediately after slicing, the slices fall into a flume or wash system that keeps them suspended and separated. Water flow and turbulence are tuned to strip off loose starch without tearing thin slices. Countercurrent wash systems can be used so cleaner water contacts cleaner slices near the exit. This reduces total water use while maintaining starch removal efficiency. After washing, slices are dewatered on vibrating screens and then passed under air knives. Dewatering is more important than it looks. A few extra grams of water per kilogram of slices can pull fryer temperature down and create a soft, oily crisp. Dewatering also reduces splatter and helps oil stay stable. The line targets a consistent surface dryness before the slices reach oil. Slicing itself is the origin of thickness consistency, and thickness consistency is the origin of uniform cook. Potatoes are fed into high-speed slicers, where rotating blades cut slices to a fixed thickness. Blade sharpness is critical. Sharp blades cut cleanly and preserve cell structure. Dull blades tear cells and create ragged edges that absorb more oil and generate more fragments. Blade condition is monitored by slice quality indicators like feathered edges and by mechanical signals like vibration and motor load. Blades are changed on schedule, so thickness and edge quality remain stable. Potato feed to the slicer is stabilized because potato size affects how the slicer loads and how slices land in the wash flume. Potatoes arrive in bulk and are graded by size. Oversized potatoes can overload slicer throats and cause thickness variation. Undersized potatoes produce small slices that fry faster and darken. Grading routes different sizes to different slicer lanes or to different product streams. The goal is to keep each slicer running within its preferred diameter range. Before slicing, potatoes are washed and often peeled depending on the crisp style. Spray washers remove soil and grit that would dull blades and darken oil. Peeling can be abrasive or steam-based. Abrasive peeling removes skin by rubbing against rough surfaces. Steam peeling loosens skin rapidly, which is then removed mechanically. Peeling choice affects yield and appearance. A peeled crisp tends to have a uniform, pale base color, while skin-on crisps show darker flecks and require tighter sorting later. Potato chemistry control is a major lever for color consistency. Reducing sugar levels in potatoes affect browning rate during frying. High reducing sugars lead to dark crisps at normal fry conditions. Plants manage this through raw material selection, blending of lots, and controlled storage temperature. Potatoes stored too cold can accumulate sugars and brown more. Potatoes stored too warm can sprout and lose solids. The plant aims for a consistent solids content and sugar level so the fryer can run at stable time and temperature. Once slices enter the fryer, the process becomes heat transfer and mass transfer. Moisture leaves the slice as steam. As water leaves, pores form. Oil replaces some of that volume as the slice cools and internal pressure drops. The factory manages oil uptake by controlling temperature, residence time, and slice thickness. Higher temperature drives faster moisture loss and can reduce total oil uptake, but it can also increase browning and fragility. Lower temperature increases residence time and oil uptake. The line balances these to hit a target oil content and color. Fryers are designed for uniformity. Oil is circulated and heated, so temperature is consistent across the belt width. Baffles guide flow to eliminate cold zones. Slice bed depth is controlled so slices are not stacked. Stacked slices insulate each other and cook unevenly. Many systems use in-feed spreaders that distribute slices into a single layer at fryer entry. Oil quality is maintained continuously. Filtration systems remove crumbs and starch fragments because they burn and darken the oil, creating off flavors and color specks. Oil turnover adds fresh oil and removes degraded oil fractions. Consistent oil quality gives consistent heat transfer and consistent browning. It also helps maintain a clean flavor profile. Color sorting is often used after frying. Optical systems detect overly dark crisps and eject them with air jets. Sorting helps manage natural raw material variation and keeps the bag consistent. It is especially useful when potatoes vary slightly in sugar content even after selection. Red Bull production begins with water being prepared before any flavor, sweetness, carbonation, or can ever enters the process. Incoming water first moves through a treatment system. It passes through filters that remove suspended particles. Activated carbon removes unwanted taste and odor. Additional polishing stages bring the water to a consistent clarity and mineral condition. The goal is a clean, neutral liquid that behaves the same way in every batch. The treated water flows into stainless steel holding tanks. These tanks are sealed and fitted with sensors that track level, temperature, and flow. Pumps draw water from the tanks and send it toward the blending area through closed sanitary pipework. A measured volume of treated water enters the first blending vessel. The agitator starts turning before the dry ingredients arrive. Its blades pull the water downward, push it outward along the tank wall, and create a steady circular movement through the entire vessel. Sugar is added into this moving water through a controlled dosing system. The crystals fall into the rotating liquid and begin dissolving. At first, the mixture looks slightly uneven. As agitation continues, the sugar disappears completely and the liquid becomes heavier, smoother, and more reflective. The sugar solution may be warmed slightly to speed dissolution. The heat is controlled because the drink must remain stable for later ingredient additions. The tank does not cook the liquid. It simply creates a smooth, sweet base with no gritty particles remaining. This sweetened base passes through fine filtration. Any undissolved material is removed before the liquid reaches the next blending stages. Clean filtration protects pumps, valves, meters, and filling equipment from blockage or uneven flow. The filtered liquid returns to the main blending line. Acid ingredients are prepared in a separate solution and metered into the moving stream. These acids give the drink its sharp, bright structure. The addition is small, but it affects the entire taste balance of the beverage. The agitator folds the acid solution through the sweet base, The liquid remains pale and clear. Unlike cola, there is no dark caramel color. Every ingredient must dissolve neatly because the finished drink has a light, translucent appearance. The functional ingredient stream is prepared next. Caffeine, taurine, vitamin components, and other formula ingredients are measured in controlled amounts. Some are added as ready-made liquid solutions. Others are dissolved in smaller preparation tanks before being pumped into the main blend. These ingredients enter through narrow stainless steel lines. Flow meters and dosing pumps control their addition. The amounts are precise because a small dosing error would affect a large volume of drink. Once added, the main agitator and inline mixers spread them evenly through the batch. Flavor concentrate is introduced after the base ingredients are dissolved. It enters as a small but powerful stream. The flavor must spread through the full tank without forming strong pockets. The mixing system keeps the liquid moving until the entire batch carries the same flavor intensity. If a colored Red Bull variety is being produced, color is added through another metered stream. A small amount changes the appearance of the whole tank. The color disperses until the liquid is uniform from the top surface to the bottom outlet. The beverage base is now sweetened, acidified, flavored, and fortified with its dissolved ingredients. It is still not finished. It has no carbonation, and its temperature is not yet ideal for filling. The blended liquid moves toward a proportioning system if the process uses a concentrated base. One pipe carries the strong blend. Another pipe carries treated water. Flow meters monitor both streams continuously. Automatic valves adjust the ratio so the final drink strength stays constant. Inside the mixing chamber, the concentrated base and treated water combine. The drink reaches its final dissolved ingredient level. It is now the correct flavor, sweetness, acidity, and appearance, but it is still flat. The flat beverage enters a heat exchanger. It flows through narrow channels inside stainless steel plates. On the other side of those plates, chilled liquid removes heat. The drink cools quickly while remaining sealed from outside air. Cold liquid absorbs carbon dioxide more efficiently than warm liquid. Cooling also prevents excessive foam during filling. If the beverage were too warm, gas would escape too easily when it entered the can. The chilled drink may pass through a deaeration vessel. Reduced pressure pulls dissolved air out of the liquid. Tiny bubbles rise and separate from the stream. Removing excess air helps the carbon dioxide dissolve more cleanly and gives the beverage more stable carbonation behavior. Carbon dioxide enters through regulated gas lines. The gas passes through pressure control equipment before reaching the carbonator. Inside the carbonator, chilled Red Bull meets carbon dioxide under pressure. The gas dissolves into the liquid, creating the sharp, sparkling texture of the finished drink. From this stage onward, the beverage stays inside closed pressurized pipes. It cannot be exposed to open air or low pressure before filling, because carbonation would escape as foam. While the drink is being made, empty aluminum cans are prepared on another line. The cans arrive already formed and printed with open tops. They are light, thin-walled, and designed to hold internal pressure after sealing. Guide rails organize them into single-file streams. The cans enter an air rinser. Curved rails invert each can. Filtered air blasts the interior to remove loose particles. The cans drain or clear, then turn upright again and continue toward the filler. The filler is a large rotary machine with many filling valves. Carbonated Red Bull enters the filler bowl under pressure. Empty cans arrive through a star wheel that spaces them perfectly beneath the valves. Each can moves into position. The filling system controls pressure and flow, so the carbonated beverage enters smoothly. The valve opens, and pale sparkling liquid drops into the can in a controlled stream. Foam is minimized by the cold temperature and pressure-balanced filling conditions. The liquid rises quickly inside the can. When the correct volume is reached, the valve closes. A small headspace remains at the top so the can can be sealed properly and hold internal pressure. The filled can moves immediately to the lid applicator. Thin aluminum lids are fed from a stacked supply and placed one by one over the open cans. The lid must arrive immediately after filling, so carbonation stays inside the package. The can enters the seaming machine. The can body and lid rotate together, while seaming rolls press the metal edges into shape. The first operation curls the lid edge around the can flange. The second operation compresses the folded metal into a tight double seam. This seam is the pressure-tight closure. It contains the carbonated drink without glue or heat sealing. The finished can leaves the seamer sealed and ready for inspection. Sensors check the fill level. Cameras inspect the lid, seam position, printed can surface, and overall shape. Seam inspection systems verify that the closure is properly formed. Any can outside tolerance is removed from the line by a fast reject mechanism. The accepted cans pass through a coding station. An inkjet printer marks production information on the base or another assigned area. The mark is applied while the can continues moving at high speed. Because the drink was chilled before filling, moisture may form on the can surface. Air knives blast thin sheets of high-speed air across the metal. Droplets are stripped from the lid, sidewall, and base. The cans must be dry before secondary packaging. The dry cans enter lane-dividing conveyors. Guide rails separate the flow into parallel rows. Timing screws and gates control spacing. Collators gather the cans into exact groups for multi-packs, trays, or cartons. For shrink-wrapped packs, plastic film feeds around each grouped set of cans. The loose bundle enters a heat tunnel. Hot air shrinks the film tightly around the can walls and pack corners. The film cools into a firm wrap that holds the cans together. For tray packs, a corrugated blank slides under the can group. Folding guides raise the sides around the base. The tray supports the cans from below. Film may then wrap around both tray and cans to create a stronger pack. For cartons, paperboard blanks feed from a magazine and fold around the grouped cans. Glue is applied to the flaps. Compression belts press the board together until the carton holds its shape. Finished packs move through inspection. Sensors check pack count, film position, carton closure, tray alignment, and code presence. Defective packs are diverted before palletizing. The accepted packs travel to the palletizer. Conveyors rotate selected packs, so each layer forms a stable pattern. A layer table gathers one full arrangement, squares the edges, and transfers it onto a pallet. Layer after layer builds upward. Each level is placed in a programmed pattern so the stack remains stable. Slip sheets may be added between layers when needed to improve load strength. Celsius production begins with a small, concentrated solution that carries the drink's functional ingredients before the full beverage volume is created. A measured amount of treated water enters a stainless steel preparation tank. The tank is smaller than the final blending vessel because this stage is built for accurate dissolution rather than high volume dilution. The agitator starts first, pulling the water into a circular motion. Powdered and liquid ingredients can then enter without forming heavy pockets at the bottom. Caffeine is measured through a controlled dosing system. It may be added as part of a prepared ingredient blend or dissolved separately before entering the main preparation stream. The amount is small compared with the final drink volume, so the dosing equipment must be precise. The ingredient enters beneath the surface and disappears into the moving water. Vitamin ingredients follow through separate feed lines or prepared solution tanks. They are added in controlled amounts and mixed until the solution is uniform. The goal is a clear, even ingredient stream that can later be diluted across thousands of cans without variation. Other formula components enter in the same controlled way. Some arrive as liquids. Some are dissolved in small side tanks before being pumped forward. The preparation tank keeps the solution moving so every ingredient spreads through the water evenly. This concentrated functional solution then passes through filtration. Fine filters remove any undissolved specks before the stream reaches the main beverage blend. The liquid must remain smooth because particles can interfere with valves, meters, and filling equipment later in the process. While this solution is being prepared, the main water stream is also being conditioned. Incoming water passes through particle filtration to remove suspended material. Activated carbon removes unwanted taste and odor. Additional polishing equipment stabilizes clarity and mineral behavior. The treated water collects in sealed stainless steel tanks where sensors monitor temperature, level, and flow. A large blending tank receives the first measured charge of treated water. The agitator begins rotating slowly, then builds a steady circulation. The tank is polished inside, so the liquid moves smoothly with no rough surfaces or dead zones. Sweetener components are added according to the product formula. In Celsius, this may involve a low-calorie or sugar-free sweetening system rather than the heavy sugar syrup used in many traditional soft drinks. The sweetener stream is dosed carefully because small amounts can strongly affect the final taste. The sweetener dissolves into the treated water. The liquid stays light and clear. It does not become thick and syrupy like a full sugar cola base. The agitator keeps the mixture uniform, while sensors track the batch condition. Acid ingredients are added next. They create the sharp, bright structure that supports the flavor. A measured acid solution enters through a closed line. The moving water pulls it downward and spreads it through the full tank volume. Flavor concentrate follows. The specific variety determines the concentrate used. Citrus, berry, tropical fruit, peach, grape, watermelon, or other flavor systems can be connected to the same blending equipment. The concentrate enters in a small stream but changes the character of the entire tank. Color ingredients are added when the variety requires them. Some formulas remain nearly clear, while others receive a light tint. The color addition is tiny, but the mixing must be complete. A small streak in the tank would become an uneven product in the cans. The concentrated functional solution now enters the main blend. It is pumped from the preparation tank through filtered stainless steel lines. Flow meters verify the addition. The liquid joins the flavored, sweetened, acidified base and is folded through by the main agitator. The beverage is now close to finished, but it still needs final dilution control and carbonation. If the plant uses a concentrate and water system, the blend moves to a proportioning unit. One pipe carries the strong beverage base. Another pipe carries treated water. The proportioner measures both streams continuously. Automatic valves make constant corrections, so the finished drink remains at the target strength. The strong base thins into the final beverage as it meets the water inside a closed mixing chamber. The flat Celsius beverage then moves into cooling. It passes through a plate heat exchanger made of thin stainless steel plates. Cold fluid moves on the other side of the plates, pulling heat from the drink. The beverage temperature drops quickly without contacting outside air. Cooling prepares the drink for carbonation. Cold liquid absorbs carbon dioxide more efficiently. It also creates a calmer filling condition later. A warm carbonated beverage would foam too heavily when it entered the can. The chilled liquid may pass through a deaeration stage. Reduced pressure pulls dissolved air out of the beverage. Tiny bubbles rise and separate from the stream. This step improves carbonation behavior by reducing unwanted gas before carbon dioxide is added. Carbon dioxide enters through regulated gas lines. Pressure control equipment stabilizes the flow before it reaches the carbonator. Inside the carbonator, chilled Celsius meets carbon dioxide under pressure. The gas dissolves into the liquid, creating the sparkling texture of the finished drink. From this point onward, the beverage remains enclosed inside pressurized piping. The liquid is finished, carbonated, and ready for the canning line. Empty aluminum cans move through a separate preparation route. They arrive already formed and printed, open at the top. The cans are lightweight, thin-walled, and shaped to hold internal pressure after seaming. Guide rails arrange the cans into a steady single-file stream. The cans enter an air rinser, where curved rails invert them. Filtered air blasts the inside surface, removing loose particles. The cans rotate upright again and continue toward the filler. The rotary filler receives the cans through a star wheel. The star wheel spaces every can beneath a filling valve. Above the valves, the filler bowl holds chilled carbonated Celsius under controlled pressure. Each can aligns with its valve. The filling system controls pressure and flow so the beverage enters without excessive turbulence. The valve opens and the sparkling drink flows into the can. The liquid rises quickly while foam is kept low by cold temperature and controlled filling conditions. The valve closes at the target fill volume. A small headspace remains at the top of the can. This space is needed for proper sealing and pressure behavior after the lid is applied. The filled can moves immediately to lid placement. Aluminum lids feed from a stacked supply. A lid separator releases one lid at a time and positions it over the open can. The can then enters the seamer. The can body and lid rotate together while seaming rolls press the metal edges into shape. The first operation curls the lid edge around the can flange. The second operation compresses the folded metal into a tight double seam. This seam seals the carbonated drink inside without glue. The aluminum folds lock together mechanically, forming a pressure-tight closure. Sealed cans move directly into inspection. Fill level sensors verify the liquid amount. Cameras check lid placement, seam condition, printed surface quality, dents, and overall can shape. Any defective can is rejected from the conveyor by an air jet or mechanical pusher. Roasted peanuts drop into a glossy caramel stream and turn it from a smooth ribbon into a textured, heavy layer. The caramel is warm, thick, and flowing slowly through a jacketed depositor. The peanuts enter at a controlled rate, so the layer has even distribution from edge to edge. Each piece becomes coated by caramel as the mixture folds through a short mixing section. The result is not a loose nut topping. It is a dense peanut caramel mass that will become the upper layer of a Snickers bar. The peanuts are prepared before they reach this point. Raw peanuts are cleaned, sized, roasted, cooled, and screened. Roasting drives off moisture and develops the nut texture. The hot peanuts pass through cooling air, so they become stable before mixing with caramel. Skins, fragments, and undersized pieces are removed, leaving a controlled peanut stream for the bar layer. The caramel begins separately in heated kettles or continuous cookers. Sugar, glucose syrup, milk ingredients, fat, and water are blended under heat. The mixture starts pale and fluid. As water evaporates, it thickens and darkens. The sugars concentrate, and the milk components help form the caramel color and cooked flavor. The caramel must be cooked to the correct body. If it is too thin, peanuts sink or spread unevenly. If it is too stiff, it will not deposit cleanly onto the nougat. The finished caramel needs to stretch during the bite, while still holding the peanut pieces in place. After cooking, the caramel moves through temperature-controlled piping. It stays warm enough to pump, but cool enough not to melt the layer beneath it. The roasted peanuts join the caramel just before depositing, so they remain separate, coated, and evenly suspended. The lower layer of a Snickers bar is nougat. Nougat starts with a cooked sugar syrup. Sugar, glucose syrup, and water are heated until the mixture reaches a high solids level. As moisture leaves, the syrup becomes thicker and more elastic. Temperature and concentration control the chew of the finished nougat. A separate aerated base is prepared in a heavy mixer. Egg albumin, or another whipping component, is hydrated and beaten until it can hold air. Hot syrup streams into this foam while the mixer turns. The heat stabilizes the foam, and the syrup strengthens it into a chewy mass. The mixture lightens as air is trapped inside. It becomes a dense confectionery foam rather than a liquid. Fat, milk components, peanut flavor elements, and other ingredients are added according to the formula. The mixer folds them in without collapsing the internal bubbles. The nougat must be soft, but not weak. It has to support the heavy peanut caramel layer above it and survive cutting later. If it is under-aerated, the bar becomes dense. If it is over-aerated, it can compress or separate under the caramel. The finished nougat leaves the mixer as a warm, elastic mass. It is transferred to a forming line. Rollers and spreading heads shape it into a wide, even sheet. Side guides keep the slab width controlled. The thickness is adjusted by calibrated rollers. The nougat sheet enters a cooling section. Cool air firms the surface and stabilizes the structure. The inside remains chewy, but the sheet becomes strong enough to carry the next layer. The peanut caramel mass now meets the nougat sheet. A wide depositor lays the warm mixture across the moving nougat. The caramel flows around the peanuts and spreads into a continuous band. Leveling equipment controls the height of the layer, so the finished bar has the right balance of nougat, caramel, and peanuts. The slab is now 2 layers moving as one. The bottom is pale, soft nougat. The top is darker caramel packed with roasted peanuts. The contrast in density is clear. The upper layer is heavier and more irregular. The lower layer is smoother and more aerated. The combined slab passes through cooling and setting. The caramel becomes less fluid. The nougat holds its shape. The peanuts lock into the caramel network. The slab must become firm enough for cutting while still remaining chewy inside. Cutting begins with lengthwise slitting. Circular knives divide the wide slab into long ropes. Each rope has the same cross-section. Nougat on the bottom, peanut caramel on top. The knives must pass through peanuts without dragging the caramel across the nougat face. The ropes are separated slightly so they do not stick back together. They then pass under a cross-cutting blade. The blade cuts each rope into individual bar lengths. The cutting action must be clean and timed with the conveyor speed. A poorly timed cut could stretch caramel strings or compress the nougat. The newly cut centers are not finished. Their sides are exposed, showing nougat, caramel, and peanuts. They need a complete chocolate coating. Before coating, the centers may travel through a conditioning zone. Air brings the surface to the right temperature. If the center is too warm, chocolate can slide or thin out. If it is too cold, chocolate can set before it spreads evenly. Milk chocolate is prepared in a separate process. Cocoa ingredients, sugar, milk powder, cocoa butter, and fats are mixed into a thick chocolate mass. The mixture passes through refining rollers that reduce particle size. This turns the chocolate from coarse to smooth. The refined chocolate moves into conching equipment. Heavy arms or rollers work the chocolate for a controlled time. The fat spreads around sugar, milk, and cocoa particles. The chocolate becomes more fluid and uniform. Before enrobing, the chocolate is tempered. It is cooled and warmed in a controlled sequence so stable cocoa butter crystals form. Tempered chocolate sets into a firm shell with the correct surface and snap. The Snickers centers enter the enrober on a wire mesh belt. A curtain of tempered milk chocolate falls from above. Each center moves through the curtain and chocolate flows over the peanut caramel top, down the sides, and across the nougat edges. Chocolate is also applied to the underside through the mesh belt. Excess coating drains through the belt and returns to the circulation system. The bar is now fully surrounded, but the shell still needs smoothing. Air blowers remove extra chocolate from the top and sides. The airflow controls coating thickness and rounds the bar's edges. It must not expose peanuts or leave thin spots. A vibrating section helps trapped air bubbles rise out of the coating and smooths the surface. The coated bars enter a cooling tunnel. Chilled air flows around them as they move forward. The chocolate changes from liquid to solid. The surface firms first, then the full shell sets around the soft center. Cooling must be controlled. Too much cold too quickly can crack the coating. Too little cooling leaves the shell soft and vulnerable to smearing. The tunnel balances air temperature, humidity, and belt speed until the chocolate is stable. At the tunnel exit, the bars pass through inspection. Cameras check shape, coating coverage, exposed center, broken peanuts at the surface, cracked chocolate, and incorrect size. Metal detectors scan the product stream. Any bar outside the programmed limits is rejected automatically. Accepted bars move to the wrapping section. Timing belts create even spacing. The bars align lengthwise before entering the flow wrapper. Printed film unwinds from a large roll. Tension rollers control its movement. Registration sensors read printed marks and synchronize the graphics with each bar. The film folds around the chocolate-coated bar through a forming box. A longitudinal seal closes along the underside or back of the wrapper. Heated sealing wheels press the film layers together. Cross-seal jaws close the front and back of each pack, sealing and cutting one wrapped bar from the next. The wrapped bars pass through check weighers. A missing, broken, or incorrect bar causes the pack to fall outside the target range. Vision systems inspect seal quality, wrapper alignment, date code position, and print registration. Defective packs are removed from the line. A coding printer applies production information to the wrapper or outer package while the pack moves at high speed. The code is small and sharp, placed in a consistent location. Reese's peanut butter cups begin with peanuts being roasted until their raw firmness turns into a brittle, aromatic center ingredient. The peanuts move through cleaning and sizing equipment first. Screens separate small fragments, dust, and oversized pieces. Airflow removes light skins and loose material. The accepted peanuts continue as an even stream toward the roaster. Inside the roaster, hot air passes around the nuts while they move through the heating chamber. Moisture leaves the peanuts. Their texture becomes drier and more fragile. The color deepens slightly, and the internal oils become easier to release during grinding. The roasted peanuts exit hot and immediately pass into cooling. Air pulls heat away so the nuts stop roasting at the intended point. If they stayed hot too long, the flavor and color would continue changing. The cooled peanuts then move through another screening stage to remove broken material and remaining skins. The prepared peanuts enter grinding equipment. Rotating plates, stones, or rollers crush them into smaller particles. At first, the peanuts break into coarse pieces. Continued grinding releases peanut oil and turns the fragments into a thick paste. The paste becomes smoother as the particles are reduced. This peanut paste is not yet the Reese's filling. It is only the base. The finished center needs a dry, sweet, slightly grainy texture that holds its shape inside the chocolate shell. The peanut paste moves into a heavy mixer. Fine sugar is added in controlled amounts. Salt follows. Other formula ingredients are added to adjust texture, sweetness, and flow. The mixer arms fold the dry ingredients into the paste. The mass thickens as sugar disperses through the peanut fat. The filling becomes firm but workable. It does not behave like a loose nut butter. It presses together as a dense filling with a sandy, smooth bite. The mixer keeps turning until the sugar, salt, and peanut paste are evenly distributed from top to bottom. Temperature control matters during filling preparation. If the mass is too warm, it spreads too easily and loses its clean shape. If it is too cool, it becomes difficult to deposit. The filling is conditioned until it can be metered in precise portions. While the filling is prepared, chocolate moves through a separate system. Milk chocolate begins as a mixture of cocoa ingredients, sugar, milk components, cocoa butter, and fats. These ingredients are blended into a thick chocolate mass. The mixture is coarse at first, so it passes through refining rollers. The rollers reduce the size of sugar and cocoa particles until the chocolate becomes smooth. The refined chocolate moves into conching equipment. Heavy mixing arms work the chocolate under controlled heat. The mass becomes more fluid as fat coats the dry particles. The texture smooths out, and the chocolate develops the flow needed for depositing into paper cups. Before use, the chocolate is tempered. It is cooled and gently reheated through a specific temperature path. This controls the cocoa butter crystals. Properly tempered chocolate sets into a firm shell with a stable surface and clean bite. The chocolate is now ready to meet the paper liners. Stacks of fluted paper cups feed into a cup placing machine. The feeder separates one liner at a time and drops it into a metal or plastic pocket on a moving belt. Each pocket holds the liner open and supports its ridged sides. Rows of empty cups travel beneath the first chocolate depositor. Heated lines keep the tempered chocolate fluid as it reaches the nozzles. The depositor releases a measured amount into the bottom of each paper cup. The chocolate spreads outward from the center. It flows into the ridges of the liner and begins forming the bottom of the cup. A vibrating section shakes the tray gently, removing trapped air and helping the chocolate level. The line may use a spreading motion to push chocolate slightly up the sides. The goal is to form a lower shell that will support the peanut butter center. The chocolate must cover the base and lower ridges evenly. The partially filled cups enter a cooling section. Chilled air passes around the trays. The chocolate firms enough to hold its shape, but it is not treated as the final shell yet. It must still bond with the top chocolate layer later. The set chocolate bases return beneath the peanut butter depositor. The filling sits in a hopper above the line. A piston or rotary pump meters the dense peanut butter mass into exact portions. Each portion drops into the center of a chocolate-lined cup. The filling does not spread all the way to the paper wall. It lands as a compact disc or mound, leaving a narrow ring of chocolate exposed around the edge. This open chocolate ring is important because the top deposit must connect with it and seal the filling inside. The peanut butter deposit may be lightly pressed or shaped as it lands. It must sit level enough for the chocolate cover to form a smooth top. If the filling is too high, it can poke through the surface. If it is off-center, one side of the cup can have too much chocolate and the other too little. The cups now move beneath the second chocolate depositor. More tempered milk chocolate flows through the nozzles. A measured deposit lands on top of each peanut butter center. The chocolate spreads across the filling and reaches the exposed ring around the edge. It joins the base shell, enclosing the peanut butter. The top layer levels into a smooth surface, while the fluted paper liner defines the outer wall. Another vibration step settles the chocolate. Tiny air bubbles rise and break. The top surface becomes flatter and more uniform. The shell, base, and cover become one continuous chocolate enclosure around the filling. The fully filled cups enter the main cooling tunnel. Cold air removes heat from the chocolate while the trays move slowly forward. The chocolate crystals stabilize. The shell firms around the peanut butter center without melting or distorting it. Cooling must be controlled carefully. If the chocolate cools too quickly, the surface can crack or lose its smooth appearance. If it cools too slowly, the cups remain soft and can smear during wrapping. The tunnel balances air temperature, airflow, and belt speed. At the exit, the cups are firm enough for handling. The paper liner holds the ridged edge. The chocolate top is set. The peanut butter center is sealed inside, still dense and soft compared with the shell. The cups pass through inspection. Cameras check top coverage, missing chocolate, exposed filling, damaged liners, broken edges, and incorrect shape. Check weighing systems verify deposit accuracy. Metal detectors scan the moving product flow. Rejected cups leave the line automatically. accepted cups move into orientation and grouping. For a standard pack, the cups are arranged in pairs. Conveyors guide individual cups into lanes. Timing belts position 2 cups side by side. The pair must remain aligned so the wrapper fits evenly and the cups do not overlap. Printed wrapper film unwinds from a roll. Registration sensors read tiny marks in the print so the design aligns with every pair. The film enters a forming section and folds around the cups. A longitudinal seal closes along the underside or back of the wrapper. Heated sealing wheels press the film layers together. Cross-seal jaws close the front and back ends. The jaws seal and cut, releasing one finished pack from the continuous film. The wrapper protects the chocolate surface and keeps the pair together. It must be tight enough to hold the cups in position, but not tight enough to crush the ridges or deform the top. Monster Energy production begins with a concentrated ingredient base being built in a stainless steel batching tank. The tank receives a small volume of treated water first. The agitator starts before the ingredient streams arrive. Its blades create a strong inward pull, drawing liquid down through the center and sending it outward along the curved tank wall. This movement prevents heavy powders or dense liquid concentrates from collecting in one place. The water used in the batch has already passed through the plant treatment system. Incoming water is filtered to remove suspended particles. Activated carbon removes unwanted odor and taste. Additional polishing stages make the water clear and consistent. The finished water is stored in closed tanks before being pumped to the blending room. The first base addition is usually the sweetener system. Sugar, glucose syrup, or another specified sweetener stream is measured into the moving water. If dry sugar is used, it falls through a controlled feeder and disappears into the rotating liquid. If liquid sweetener is used, it enters as a thicker stream and folds into the water as the agitator turns. The sweetened liquid becomes denser. The surface changes from fast ripples to slower, glossy movement. Temperature may be raised slightly to help the sweetener dissolve, but the liquid is not cooked. The goal is a clear, smooth base that can carry the rest of the formula without gritty particles. This sweet base passes through fine filtration. The filter removes any undissolved sugar or small particles before the liquid reaches the precision ingredient area. Clean flow is important because later equipment depends on accurate metering through valves, pumps, and flow sensors. The filtered base returns to the main blending vessel. Acid ingredients are added through a metered line. They create the sharp structure behind the sweetness. The acid stream is small compared with the full batch volume, so it must be spread evenly. The agitator keeps the liquid moving until the acidity is uniform throughout the tank. The energy ingredient blend is prepared next. Caffeine, taurine, B vitamin components, and other formula ingredients are measured in smaller preparation vessels. Some ingredients arrive as liquids. Others are dissolved into water first, so they can enter the main tank as controlled solutions. Each addition is pumped through closed stainless steel lines. Flow meters track the amount. The ingredient streams enter beneath the surface, where the moving liquid immediately pulls them through the batch. The tank must distribute them evenly because the finished drink is filled at very high speed, with no chance to correct uneven concentration later. Flavor concentrate is then introduced. Monster varieties use different flavor systems depending on the product, so the same blending equipment can produce different versions by changing the programmed concentrate, color, and ingredient sequence. The concentrate enters in a small, powerful stream. The tank darkens, brightens, or shifts color depending on the variety. Color is metered separately when required. A small amount spreads through the entire batch and changes the appearance of the liquid. Greenish, golden, orange, blue, purple, or near clear varieties can be produced by changing this stream and the flavor system connected to it. The concentrated base is now strong, sweet, acidic, flavored, and loaded with dissolved ingredients. It is not yet the final beverage. It may be too concentrated for direct filling, so it moves toward a proportioning system where it will be diluted to finish strength. A second stream of treated water arrives from storage tanks. This water bypasses the small concentrate tank and moves directly toward the final blender. Flow meters measure both streams. One meter reads the concentrate flow, another reads the treated water flow. The proportioner adjusts both streams continuously. Automatic valves make small corrections whenever pressure or flow changes. The machine keeps the ratio locked so the drink has the same flavor strength, sweetness, acidity, and dissolved ingredient level from the first can to the last. Inside the final blending chamber, the concentrate and water combine. The intense base thins instantly. The drink reaches its final formula strength. At this stage, it is flat Monster Energy. It has color, sweetness, acidity, flavor, and dissolved energy ingredients, but it has no carbonation. The flat beverage flows into a cooling section. It passes through a plate heat exchanger, moving through narrow channels between stainless steel plates. Chilled fluid travels on the opposite side of the plates and pulls heat out of the drink. The beverage temperature drops quickly while the liquid remains sealed from outside air. Cooling prepares the drink for carbonation. Cold liquid absorbs carbon dioxide more effectively than warm liquid. Cold filling also helps reduce foam when the beverage enters the can. Before carbon dioxide is added, the beverage can pass through a deaerator. Reduced pressure pulls dissolved air out of the liquid. Tiny bubbles rise and separate from the stream. Removing excess air allows carbonation to behave more predictably and helps the drink stay consistent inside the sealed can. Carbon dioxide enters through pressure-regulated gas lines. The gas is filtered and controlled before reaching the carbonator. Inside the carbonator, chilled Monster Energy flows under pressure while carbon dioxide dissolves into it. The liquid becomes sparkling, but the gas remains trapped in solution because the system stays sealed and pressurized. From this point forward, the beverage must stay under controlled pressure. It moves through closed stainless steel piping toward the filler. Any sudden pressure drop would cause foaming and carbonation loss. While the drink is being blended and carbonated, empty cans move on a separate line. The aluminum cans arrive already formed, decorated, and open at the top. They are light, thin, and designed to hold internal pressure once sealed. The cans enter a lane-guided conveyor and move toward the rinser. Curved tracks invert each can. Filtered air blasts the interior to remove loose particles. The cans rotate upright again and continue toward the filling machine. They move in tight rows, with rails keeping them stable as they approach the star wheel. The rotary filler receives the cans one by one. The star wheel spaces them evenly and positions each can beneath a filling valve. Above the valves, the filler bowl contains chilled carbonated Monster under controlled pressure. The filling valve opens. The drink flows smoothly into the can. The liquid must enter without excessive turbulence. If it splashes too hard, foam rises and interferes with the fill level. The cold temperature and controlled pressure keep the fill clean. The can fills rapidly. A small headspace remains at the top. This space is necessary for proper sealing and pressure behavior after the lid is applied. The valve closes at the exact target volume, and the can moves immediately towards seaming. Aluminum lids feed from a stacked supply. The lid dispenser separates one end at a time and places it over each filled can. The can cannot remain open for long because carbonation would begin escaping. The seamer closes the package mechanically. The can body and lid rotate together. The first seaming roll curls the lid edge around the can flange. The second roll compresses the metal folds into a tight double seam. No glue is used. The pressure-tight seal is created by folded aluminum. The sealed cans travel directly into inspection. Fill level sensors verify the liquid amount. Cameras check the lid, sidewall, top surface, and printed body. Seam inspection systems examine the double seam. A can with a dent, low fill, high fill, weak seam, or missing code is rejected from the line. The accepted cans pass through a coding station. An inkjet printer marks the can with production information. The code is applied to the base or another assigned area while the can moves at full conveyor speed. Because the drink was chilled before filling, condensation can form on the can surface. Air knives blast narrow sheets of high-speed air across the lid, sidewall, and base. Water droplets break away so the cans enter, packaging dry. The dry cans move into lane dividers. Guide rails split the flow into parallel rows. Timing screws control spacing. Stop gates and collators gather cans into the correct pattern for secondary packaging. 7-Up production begins with a clear, lemon-lime base that must stay bright, transparent, and free of visible particles from the first mixing stage. Treated water enters the blending room through closed stainless steel pipework. Before it reaches the tank, the water has already passed through filtration stages that remove suspended particles. Carbon treatment removes unwanted taste and odor. Final polishing creates a consistent liquid base that will not interfere with the clean lemon-lime flavor. The treated water collects in a sealed storage tank. Sensors measure level, temperature, and flow. A pump sends a controlled volume into the main dissolving vessel. The tank interior is smooth and polished, so the liquid can circulate without dead spots. The agitator begins turning before sweetener is added. Its blades pull the water downward and drive it outward in a steady loop. This motion prepares the tank for sugar, liquid sweetener, or another specified sweetening system. Sweetener enters through a dosing line. If granulated sugar is used, the crystals fall into the moving water and dissolve as the liquid rotates. If liquid sweetener is used, it flows in as a dense stream and blends into the water more quickly. The tank keeps the liquid moving until the base is uniform. The sweetened liquid remains clear. It does not darken like cola syrup or become opaque like some fruit-flavored drinks. The mixture becomes slightly heavier and glossier, but it must keep a clean appearance. The sweet base passes through fine filtration. Small undissolved particles are removed before the beverage reaches flavoring and carbonation equipment. This protects the later valves and meters, but it also helps preserve the transparent look of the finished drink. A lemon-lime flavor concentrate is prepared in a separate dosing system. It is strong, aromatic, and added in a small amount compared with the full batch volume. Metering pumps push it through a narrow stainless steel line into the moving sweet base. The concentrate disappears into the tank without changing the liquid into a dark or cloudy drink. The agitator folds the flavor through the full volume. Because 7-Up is a clear soda, the flavor components must disperse evenly and remain stable without visible separation. Acid ingredients are introduced next. They create the sharp citrus structure that balances the sweetness. The acid stream is metered into the tank below the surface, where the moving liquid immediately pulls it through the base. The liquid is mixed until sweetness, acidity, and flavor strength are consistent. The tank does not rely only on time. Flow meters, temperature readings, and recipe controls keep the batch inside its target range. At this stage, the beverage base is strong and still. It has lemon-lime flavor, sweetness, and acidity, but it may not yet be at final drinking strength. If the process uses a concentrated syrup system, the base moves to a proportioner. The proportioner receives 2 streams. One stream carries the strong lemon-lime syrup. The second stream carries treated water from storage. Each stream passes through a flow meter before blending. The machine constantly compares the 2 flows. If the water stream rises, the syrup stream adjusts. If syrup pressure shifts, the water valve corrects. This keeps the final ratio stable across thousands of bottles or cans. Inside the blending chamber, the syrup thins instantly. The drink reaches finish strength while remaining clear and flat. It has no sparkle yet. It is still a non-carbonated lemon-lime beverage at this point. The flat 7-Up moves into cooling equipment. It passes through a plate heat exchanger. The beverage travels through narrow channels between stainless steel plates. A chilled medium moves on the opposite side of those plates and pulls heat away. The temperature drops quickly. Cooling is essential because cold liquid absorbs carbon dioxide more efficiently. It also fills more cleanly later, with less foam and less gas loss. The beverage may pass through a deaeration vessel. Reduced pressure draws dissolved air out of the liquid. Tiny bubbles rise from the stream and separate before the drink continues. Removing excess air gives carbon dioxide more room to dissolve and helps the finished soda behave consistently. Carbon dioxide enters through regulated gas lines. The gas passes through pressure control equipment before reaching the carbonator. Inside the carbonator, cold 7-Up meets carbon dioxide under pressure. The gas dissolves into the liquid, forming the sharp, sparkling bite. The drink is now finished and carbonated. From this point onward, it stays in closed pressurized pipes. The system keeps the gas inside the liquid until the container is sealed. While the beverage is being prepared, empty containers are moving through their own lines. For plastic bottles, the process begins with PET preforms. These are short, thick plastic tubes with finished neck threads. The neck is already complete. The body is still compact and must be expanded into the final bottle shape. The preforms enter a heating oven. Infrared lamps warm the plastic body as each preform rotates. Rotation prevents one side from heating faster than the other. The neck area stays cooler, so the threads and sealing surface keep their exact dimensions. A heated preform moves into a blow mold. The mold closes around it. A stretch rod drives downward through the softened plastic, pulling it lengthwise. Compressed air then expands the plastic outward against the chilled mold wall. The bottle forms instantly. The base, shoulders, grip panels, and label area appear as the plastic presses into the mold. The mold opens, and the empty bottle exits by its neck ring. The bottles move through air conveyors toward rinsing. Because the bottles are very light before filling, they are supported by the neck rather than pushed heavily along the base. Airflow moves them forward in a controlled stream. At the rinser, each bottle is gripped, inverted, and cleaned internally with filtered air or treated rinse water. The bottle drains, rotates upright, and moves toward the filler. Can lines prepare a different container? Aluminum cans arrive already shaped and printed with open tops. They pass through an air rinser, turn upside down, receive a blast of filtered air, and return upright before filling. Glass bottle lines begin with formed bottles. Cameras and light systems inspect the mouth, base, sidewall, and interior. Any bottle with a crack, chip, or visible defect leaves the line before filling. The carbonated 7-Up arrives at the filling machine through pressurized piping. The filler is a rotary carousel with many filling valves arranged around a central bowl. Containers enter through a star wheel that spaces them precisely. Each bottle or can aligns under a filling valve. Because the drink is carbonated, the filling system controls pressure before liquid enters. The container is sealed against the valve, and internal pressure is balanced with the filler environment. The valve opens. Clear sparkling 7-Up flows into the container. In a transparent bottle, the liquid rises almost invisibly, except for the fine bubbles forming along the wall. The fill level reaches the programmed height, and the valve closes. The filled container moves immediately to sealing. Plastic bottles travel under capping heads. Caps arrive from a sorter in the correct orientation. Each head places one cap on the threaded neck and tightens it to a set torque. The tamper band locks below the neck ring. Cans move into a seamer. A thin aluminum lid is placed over the filled can. The can and lid rotate together while seaming rolls fold the lid curl around the can flange. A second roll compresses the folded metal into a tight double seam. Glass bottles receive crown caps. The capper presses a metal crown onto the mouth and crimps its edge beneath the glass bead. The closure traps carbonation inside the bottle. Sealed containers pass through inspection. Fill level sensors check the amount of liquid. Cameras examine caps, crowns, can seams, bottle shape, and printed surfaces. Low fills, high fills, crooked caps, weak seams, and damaged containers are rejected automatically. Bottles move toward labeling after inspection. Since 7, up is clear, bottle and label alignment matter visually. The label must sit evenly around the container without covering the wrong panel or twisting across the body. For roll-fed labels, printed film unwinds from a reel. Registration sensors locate the print marks. A cutter separates each label. Adhesive attaches the leading edge to the bottle, and the bottle rotates as the film wraps around it. The trailing edge is sealed into place. Some formats use pressure-sensitive labels. These peel from a backing web and press onto the bottle through soft rollers. Glass bottles may receive glued paper labels that are brushed flat as the bottle turns. Cans usually arrive with their design already printed on the metal, so they move directly toward coating and packing after seaming and inspection. Coating equipment marks each container. Inkjet printers place production information onto the cap, bottle shoulder, label, can base, or glass surface. The code appears in a fraction of a second while the container remains in motion. Cold filling can create condensation on the outside. Air knives remove it. High-speed sheets of air strike the cap, shoulder, sidewall, seam, and base. Dry containers continue more reliably into packaging machinery. Poppy production begins with a sharp apple cider vinegar ingredient stream being measured into a much larger beverage base. The vinegar is not added loosely. It moves through a controlled dosing line with pumps measuring the amount before it enters the blending system. Because the flavor is strong and acidic, the dose must spread evenly through the full batch. The tank is already moving before the stream enters. Treated water is the main liquid. Incoming water passes through filtration to remove suspended particles. Carbon filtration reduces unwanted taste and odor. Final polishing stages create a clear, neutral base. This water is stored in sealed stainless steel tanks before blending. A measured quantity of treated water enters the main blend tank. The agitator starts turning below the surface. Its blades pull the water downward and push it outward along the tank wall. The movement creates a full tank circulation pattern, so later additions do not remain concentrated in one area. The apple cider vinegar stream enters beneath the surface. It folds into the moving water and quickly disperses. The acidity changes the base before sweetener or flavor is fully built. The liquid remains clear, but its sharp profile is now established. Sweetener is added next. Poppy-style drinks usually use a lighter sweetening system than a full sugar soda, so the sweetener amount is much smaller than in a traditional syrup room. The sweetener may enter as a liquid solution or as a prepared blend that dissolves quickly. The agitator continues moving. Sweetness spreads through the acidic water and softens the sharp edge of the vinegar. The base becomes balanced enough to carry fruit flavor, but it is still flat and uncarbonated. Prebiotic fiber ingredients are prepared carefully because they must dissolve cleanly and remain stable in the drink. A small preparation tank may receive treated water first. The fiber ingredient is added slowly while mixing prevents clumps. Once fully dispersed, this solution is pumped into the main blend. The fiber stream enters through a closed line. Flow meters confirm the addition. The main tank pulls the stream into circulation and spreads it through the beverage. The liquid must stay smooth, with no visible particles or thick sections. Acid balance is adjusted after the vinegar and fiber stream are in the tank. Fruit-flavored sparkling drinks need a controlled bright taste, not a harsh one. Additional acid or buffering ingredients can be metered in depending on the flavor. The tank mixes until the liquid reaches a uniform base condition. Flavor concentrate enters through another dosing line. Strawberry lemon, raspberry rose, orange, grape, cherry limeade, watermelon, or other varieties can be produced by changing the concentrate connected to the blending system. The concentrate is small in volume but strong in effect. The flavor stream hits the moving liquid and disappears. The tank turns the sharp, lightly sweetened base into a specific flavor profile. The mixture must be uniform before carbonation because once the drink is in pressurized piping, there is little opportunity for heavy correction. Color ingredients may be added depending on the variety. Some poppy drinks remain lightly tinted. Others take on a brighter fruit color. The color stream is metered in carefully. A very small amount changes the entire tank, so mixing continues until no streaks remain. The beverage base now contains treated water, vinegar, sweetener, fiber solution, acid balance, flavor, and color. It is still not finished. It must be clarified through filtration or strainers if the formula requires it, then chilled and carbonated. The liquid moves through a fine filtration stage. This step removes undissolved specks and protects later valves and filler nozzles. The drink must remain clean and smooth as it travels through high-speed equipment. The filtered base flows into a balance tank before final processing. Pumps pull from this tank and send the beverage toward cooling. Flow remains steady so the carbonation system receives an even supply. The drink enters a plate heat exchanger. It travels through narrow stainless steel passages. On the other side of the plates, a chilled medium removes heat. The beverage temperature drops quickly while the liquid remains sealed inside the system. Cold liquid absorbs carbon dioxide more efficiently than warm liquid. Cooling also reduces foam when the beverage enters cans. This is important because poppy is packaged as a sparkling drink, and uncontrolled foam would interfere with accurate fills. The chilled beverage may pass through a deaerator. Reduced pressure pulls dissolved air out of the liquid. Tiny bubbles rise and separate from the stream. Removing excess air helps the carbon dioxide dissolve more cleanly and keeps the drink's carbonation consistent. Carbon dioxide enters through regulated gas lines. Pressure control equipment stabilizes the gas before it reaches the carbonator. Inside the carbonator, chilled poppy meets carbon dioxide under pressure. The gas dissolves into the drink and creates the sparkling texture. From this point onward, the beverage stays inside pressurized stainless steel piping. The system keeps carbon dioxide dissolved until the can is sealed. The finished drink travels directly toward the filler. Empty aluminum cans move on a separate line. They arrive already formed, decorated, and open at the top. The cans are thin and lightweight, but they are designed to hold internal pressure once sealed. Guide rails organize the cans into single-file movement. The cans enter an air rinser. Curved tracks turn each can upside down. Filtered air blasts the inside, removing loose particles. The cans rotate upright again and continue toward filling. The rotary filler receives the cans through a star wheel. The star wheel spaces every can beneath a filling valve. Above the valves, the filler bowl holds chilled, carbonated poppy under controlled pressure. Each can reaches its valve. Pressure and flow are controlled so the drink enters smoothly. The valve opens and the sparkling liquid flows into the can. Foam is held low by the cold temperature and the controlled filling environment. The fill level rises quickly. When the target volume is reached, the valve closes. A small headspace remains at the top. This space allows the lid to be applied and the sealed can to hold carbonation properly. The filled can moves immediately to lid placement. Aluminum lids are fed from stacked magazines. A lid separator releases one lid at a time and places it over the open can. The can enters the seamer. The can body and lid rotate together. The first seaming roll curls the lid edge around the can flange. The second roll compresses the folded metal into a tight double seam. The seal is mechanical, created by folded aluminum rather than glue. The sealed can exits with the sparkling drink trapped inside. Inspection begins immediately. Fill level sensors check the amount of liquid. Cameras examine lid placement, printed surface condition, dents, and overall can shape. Seam inspection checks the closure profile. A defective can is rejected by an air jet or mechanical pusher. Accepted cans continue in a steady stream toward coating. An inkjet printer marks production information on the can base or another assigned location. The code is applied while the can moves at full speed. A vision system can verify that the code is present and readable. The defining feature of a Krispy Kreme-style ring donut is the thin, tender crust and airy interior that come from a dough that is proofed to a narrow endpoint, fried with a controlled flip, then glazed while the surface is still warm enough to accept a uniform film without soaking. Everything is organized around the proof-to-fry handoff, so the line is built to keep dough pieces moving continuously from cutting to proofing to oil without waiting. The dough system starts with flour and liquid staged to produce a consistent final dough temperature. Flour is sieved to remove lumps and to stabilize flow into the mixer. Sugar is screened so crystal size does not vary significantly because sugar affects both fermentation rate and browning. Salt is weighed precisely to control dough strength and yeast activity. Yeast is prepared as a dry addition or slurry, so it disperses evenly. Fat is tempered so it blends smoothly without streaking. Water and dairy liquids are tempered because final dough temperature is one of the strongest predictors of proof time. Mixing builds a gluten network that can expand without tearing. The mixer begins at low speed to hydrate flour and incorporate yeast and sugar uniformly, then increases speed to develop gluten to a target elasticity. The target is not maximum strength. The dough must be strong enough to hold gas during proofing and frying, but extensible enough to sheet cleanly and cut without shrink. Fat is introduced after initial gluten development, so it softens the network rather than blocking formation. The mix endpoint is judged by dough smoothness and elasticity and by temperature. If the dough exits too warm, it will ferment too fast and become sticky on rollers. If too cool, it will be tight and resist expansion. After mixing the dough, enters a short rest to equalize moisture and relax gluten. Relaxation reduces snapback in sheeting, which is essential for ring accuracy. During this rest, early fermentation begins creating small gas cells. The rest is timed so the dough remains workable and does not overexpand before forming. Forming begins with sheeting. The dough passes through a series of reduction rollers that gradually decrease thickness. Large reductions are avoided because they create stress lines that show up as weak spots during frying. Gauge rollers at the end set the final sheet thickness, and that thickness becomes a primary determinant of donut weight and final crumb thickness. The sheet then enters rotary cutting, where an outer ring and an inner hole are cut in one motion. Cutter sharpness is critical because dull cutters compress the edges and create ragged rims that absorb more oil and brown unevenly. Scrap dough around the cutouts is lifted and recycled at controlled ratios because heavy recycling increases work input and changes dough strength. Cut rings are transferred onto proofing screens or belts with minimal distortion. Transfer height is kept low, and the dough is supported so it does not stretch. Stretching changes ring thickness and causes uneven expansion. The rings then enter the proofer, which is essentially a controlled fermentation chamber that raises the dough to near final volume. Proofing conditions are set to achieve rapid, even expansion without forming a surface skin. Temperature controls yeast activity. Humidity prevents the surface from drying and sealing, which would trap expanding gas and cause blisters. Proof time is tuned so the ring becomes light and inflated, yet still strong enough to be moved and flipped in oil. Underproof produces dense donuts with thicker crust and less lift. Overproof produces fragile rings that collapse when they hit the fryer or when they are turned. The fryer is designed to set the structure quickly while preserving a thin crust. Oil temperature is held in a narrow band and monitored continuously. When proofed rings enter the oil, surface water flashes to steam, creating outward pressure that expands the ring further and helps delay oil penetration in the earliest seconds. Starch gelatinizes at the surface and forms the initial crust. Proteins coagulate and lock structure. As the surface dries, browning begins and color develops. Rings typically fry one side first while floating. Conveyor speed sets the dwell on the first side, then a turning mechanism flips the ring. Flip timing is a major control because the first side must be set enough to support the ring during rotation, but not so overcooked that it becomes thick and dark. After the flip, the second side fry completes structure set and balances moisture loss. The total fry time is tuned to yield a pale, thin crust that remains tender rather than thick and crunchy. Oil management is continuous because crumbs and fragments break off and burn, darkening oil and changing heat transfer. Filtration removes fines. Oil circulation maintains uniform temperature across the fryer width. Fresh oil addition and controlled bleed maintain quality, so color remains consistent from hour to hour. Stable oil behavior is essential because even small changes in heat transfer shift crust thickness and glaze pickup. As rings leave the fryer, surface oil drains immediately. Drain belts and brief vibration shake off free oil. Removing surface oil matters because it affects glaze adhesion and prevents greasy patches that repel glaze. The donuts then move onto a short cooling conveyor, but the cooling is not intended to fully cool them. It is intended to bring the surface into the glaze window. Glaze is applied while the donut is still warm. The glaze is a sugar solution or suspension mixed to a defined solids level. Solids level determines film thickness and set speed. The glaze is held warm enough to flow smoothly, but not so hot that it becomes too thin. Donuts enter a glaze waterfall or curtain where glaze coats the surface. Excess glaze drains as donuts travel on a belt. The warm donut surface helps the glaze spread evenly and then set. If donuts are too hot, glaze becomes excessively thin and runs off, leaving a patchy coat. If too cool, glaze sets too quickly and creates uneven coverage and a grainy texture. After glazing, the donuts move through a setting zone where glaze crystallizes. Airflow here is controlled because strong airflow can dry glaze too fast and create a rough finish, while weak airflow can leave glaze tacky and prone to sticking in cartons. The objective is a smooth, thin glaze shell that remains slightly delicate and glossy. For filled products, filling is typically done after the donut has cooled further and the crust has stabilized. A controlled injection system uses needles to place a measured dose of filling. Filling viscosity is tuned so it flows through needles without tearing the crumb and then holds shape without leaking. Needle depth and dose volume are controlled so filling is distributed without blowouts. If a cut and fill format is used, a slit is made and a nozzle deposits filling into the cavity, then the surface is finished and allowed to set. Chocolate icing or other coatings are applied after glazing or instead of glazing depending on format. These coatings are typically fat-based and set by cooling rather than crystallizing like sugar glaze. Coating temperature and viscosity determine thickness and surface smoothness. Toppings are applied while the coating is tacky so they adhere before the surface sets. Packaging and handling are built to protect the glazed surface, which can mark easily. Donuts are typically loaded into cartons that prevent stacking pressure on the glaze. Carton loading uses guides that minimize contact with the top surface. If the product is individually wrapped, the donuts must be fully set and cooled to avoid condensation inside the wrap and to avoid smearing. Wrap films are selected to manage moisture because donuts dry out quickly if exposed to air. Snickers manufacturing can be understood from the cutter backward because the entire line is built to deliver a layered slab that is firm enough to slice cleanly, stable enough to ride through a chocolate curtain, and uniform enough that every bar finishes at the same weight. At the cutter, the slab must present a flat top surface, a consistent total thickness, and a predictable resistance to the knife. If the slab is too soft, caramel smears and drags, nuts dislodge, and edges tear. If the slab is too hard, the caramel fractures and the nougat can crack into ragged faces that later create coating voids. The plant therefore shapes and cools each layer so the combined slab reaches a narrow cut, window before portioning begins. The slab is built on a continuous belt. The bottom layer is aerated nougat. Nougat begins with two inputs that are prepared separately so they can be combined without collapsing the bubble structure. A cooked syrup that defines solids and elasticity, and a foam phase that carries metered air. Syrup cooking starts with sugar and glucose syrup streams that are metered into a cooker and concentrated. The cook endpoint sets the moisture level in the final nougat. A higher moisture syrup yields a softer nougat that can slump under the caramel layer. A lower moisture syrup yields a tighter nougat that becomes chewy and resists cutting. The cooker is operated to a precise endpoint and the syrup is delivered forward at a controlled temperature so it strengthens foam but does not scorch it. The foam phase is produced from a protein solution. The solution is mixed to a defined concentration and fed to a continuous aerator. Air is metered in, and shear is applied to create small, uniform bubbles. Bubble size distribution matters because large bubbles collapse and create voids, while small bubbles create a smooth, light texture. Density is measured continuously because density is the direct control for nougat weight and bite. If density drifts, the finished bar weight drifts. Syrup and foam merge in a continuous mixer designed to fold rather than whip. Folding distributes syrup through foam without breaking bubbles. Syrup heat partially sets the protein films and locks the microcell structure. Fat is injected as a thin stream to soften bite and reduce stickiness. Emulsifiers can be added in small doses to stabilize the air-fat sugar system and improve flow at the depositor. The mixed nougat exits as a warm, aerated mass with controlled viscosity. Nougat is deposited onto the moving belt as a continuous slab. A spreader head lays down a wide band, and gauge rollers set thickness. Thickness control is critical because it defines the core height and influences later cooling time. The slab enters a cooling tunnel with staged zones. Early zones firm the surface enough to support caramel deposition. Later zones remove heat more gradually so the interior firms without forming a brittle skin. The target exit condition is a nougat slab that is firm but still receptive at the surface so caramel can bond. Caramel is prepared in a separate stream because it requires different cooking and different set behavior. Sugar and glucose syrup are cooked with dairy components to develop caramel notes and reach an elastic solids endpoint. The endpoint determines whether caramel behaves as a clean sheet or as a smear. Too low solids and caramel drags on knives. Too high solids and caramel fractures, especially when nuts create stress points. Fat is added to smooth the matrix and reduce tack. The caramel is cooled to a working temperature where viscosity is stable for deposition and held in jacketed tanks with gentle agitation to prevent skin formation. Peanuts are prepared as a topping stream that must spread evenly and remain dry. Roasted peanuts are screened to remove fines and broken pieces. Fines create dust and uneven coverage. Oversized pieces create peaks that cause thin chocolate spots later. The peanuts are cooled after roasting so they do not warm the caramel surface and change tack behavior. They are stored in dry conditions so they flow freely through spreaders. Layering begins when the nougat slab reaches the caramel station. Caramel is deposited as a continuous layer using a slot head. A leveling bar spreads it to uniform thickness. Temperature matching is essential. If caramel is too hot, it softens the nougat surface and creates a weak interface. If too cool, it does not fuse and can delaminate later. The line targets a condition where caramel wets the surface slightly and then begins to set as it moves forward. Immediately after caramel deposition, peanuts are applied. A spreader distributes nuts across the full width at a controlled mass flow. Distribution must be uniform, so every bar receives a similar nut density. A light pressing station can embed nuts slightly into caramel to improve mechanical lock. Pressing is controlled to avoid crushing nuts and to avoid squeezing caramel sideways, which would create thick edges and thin centers. After nut application, the slab enters a conditioning zone. This zone firms the caramel layer enough for cutting and locks nut position, so nuts do not slide when the slab is later accelerated. Cooling is staged to avoid differential contraction between nougat and caramel, because differential contraction can cause the slab to curl. Curling leads to uneven coating thickness and cutting errors. The slab is held flat by belt support and cooled to a target firmness. Edge trimming removes uneven edges where thickness variation is most common. Trim is collected for controlled rework streams. The main slab then enters lane cutting. Rotary knives slice the slab into long lanes of constant width. A crosscutter then slices lanes into bar lengths. Knife timing is synchronized to belt speed to maintain consistent weight. Knife surfaces are managed to reduce caramel buildup that would tear edges. Clean edges are important because ragged edges trap air under the chocolate curtain and cause voids. The cut bars are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges. Transfer points are designed with minimal drop height because impact can dislodge nuts and dent nougat. A brief pre-chill can be used to firm the surface and improve chocolate coverage. Pre-chill is balanced so the bars do not become so cold that condensation forms when they enter warmer chocolate equipment. Chocolate coating is prepared and held in a tempering loop. Chocolate is melted and filtered to remove unmelted fragments. Tempering creates a stable seed crystal population through controlled cooling and reheating. Working temperature is maintained tightly because viscosity defines curtain thickness and coat weight. Viscosity that drifts too high produces heavy coatings and thick feet. Viscosity that drifts too low produces thin coatings and exposed corners. Enrobing coats the bars with a top curtain and a bottoming system. The top curtain covers the top and sides. The bottoming system coats the underside, sealing the bar and protecting caramel from exposure. Excess chocolate drains through a wire belt. Air knives smooth the surface and control foot thickness. Air knife settings are tuned so they remove excess without exposing nut peaks at corners. If a top drizzle pattern is required, it is applied immediately after enrobing while the surface is still tacky. A stringer deposits thin lines that bond to the base coat. The bars then enter the cooling tunnel. Cooling is staged to set the chocolate and preserve surface quality. The first zone sets the surface quickly so the coating does not slump and nuts do not shift. Subsequent zones cool more gradually to promote stable cocoa butter crystals and reduce bloom risk. Tunnel humidity is controlled to prevent condensation that would cause sugar bloom and dullness. Bars exit the tunnel at a temperature suitable for wrapping with a coating hard enough to resist scuffing. After cooling, inspection checks coating coverage, shape, and weight. Vision systems detect exposed edges and coating voids. Weight checks confirm portion control across cutting and coating. Bars outside tolerance are diverted. Chocolate rework is remelted and returned upstream. Nougat and caramel rework is handled separately because their aeration and moisture differ from fresh streams. Wrapping begins once bars are fully set. Flow wrappers form film around each bar and seal it with controlled heat and dwell time. Film tension is controlled to avoid scuffing the coating. Coating is applied for traceability. Wrapped bars are collated into multi-packs or cartons, then case packed. Lay's-style potato chips are manufactured by controlling three things more tightly than anything else: slice geometry, surface starch, and oil temperature. When those three are stable, the process reliably turns raw potatoes into thin, brittle chips that drain cleanly, accept seasoning evenly, and stay crisp inside a sealed bag. The line is easiest to follow from the seasoning drum backward because seasoning performance tells you whether the upstream steps produce the right surface. Chips that are too wet reject powder and clump. Chips that are too dry fracture into excessive fines. Chips that carry excess surface oil feel greasy and carry seasoning unevenly. The factory therefore builds chips so they exit the fryer with a narrow moisture and oil window before they ever reach flavor application. The final steps start at de-oiling. Chips exit the fryer on a mesh conveyor and immediately pass over vibrating drains. Vibration shakes off free oil while the chips are still hot and rigid enough to tolerate movement. Air knives or blowers can strip oil film from the surface and from curled edges. This is not a cosmetic step. Excess surface oil can cause seasoning to clump and can also migrate into the bag headspace, increasing the perception of greasiness. De-oiling settings are tuned so oil is removed without cracking the chips into fragments. From de-oiling, chips flow into a rotating seasoning drum. The drum provides gentle tumbling, so every chip surface is exposed. Seasoning is dosed as a fine powder or a blend and is metered by mass flow to match chip throughput. Adhesion relies on a thin oil film that remains on the chip surface. Too much film causes heavy seasoning pockets. Too little film yields bare chips. Drum speed and fill level are adjusted so chips roll rather than slide, because rolling distributes seasoning and minimizes breakage. A short dwell time allows seasoning to distribute fully without grinding chips into fines. Immediately after seasoning, chips move toward packaging, but they first pass through screening. Screens remove small fragments and fines produced by slicing and frying. Removing fines improves bag appearance and also prevents seals from being contaminated by dust. Fines also absorb more oil and can go stale faster, so their removal improves consistency. Packaging begins with portioning into bags using multi-head weighers. Chips are lightweight and irregular, so the weigher uses multiple small hoppers and selects combinations that hit target weight. Drop paths are designed to reduce breakage. Bags are formed from barrier film that resists oxygen and moisture transmission. Nitrogen flushing is commonly used to displace oxygen and to create headspace that cushions chips. The bag is sealed with heat and pressure. Seal parameters are tuned so seals hold without wrinkles that would leak. All of those downstream steps assume chips arrived with the correct structure, which is created in the fryer. Frying is not just cooking. It is a controlled dehydration process that forms a rigid, porous matrix. Chips enter hot oil and water at the surface flashes to steam. Steam leaves through the sliced surfaces, creating pores and crispness as moisture content drops. Oil temperature is held in a narrow band because it controls how fast water leaves and how much oil enters. If oil is too cool, chips stay in the fryer longer, absorb more oil, and remain flexible rather than crisp. If oil is too hot, the surface can brown before moisture leaves evenly, producing dark edges and fragile structure. Residence time in the fryer is controlled by conveyor speed and by chip bed depth. Bed depth matters because too deep a layer reduces oil contact and yields uneven color. Oil circulation is designed to keep temperature uniform across the fryer. Filters continuously remove crumbs and starch fragments that break off. Without filtration, crumbs burn and darken the oil, increasing dark specks and changing heat transfer. Oil turnover with fresh oil additions maintains consistent frying behavior over long runs. Before frying, slices go through a washing stage that controls surface starch. Freshly sliced potatoes release starch that forms a sticky film. If that film remains, slices stick together in the fryer and cook unevenly. The wash system uses flumes and sprays to remove free starch. Flow is tuned so slices separate without breaking. After washing, slices are dewatered on vibrating screens and with air knives. Removing surface water matters because water entering the fryer cools the oil locally and increases splatter and oil breakdown. Dewatering stabilizes fryer temperature and improves chip texture. Slice geometry is set at the slicer and influences every downstream step. Potatoes are fed into a high-speed slicer where a rotating blade cuts thin slices at a fixed thickness. Thickness is the primary determinant of crispness and color. Thinner slices cook faster and become very crisp, but can be fragile. Thicker slices cook slower and can remain slightly chewy if the fryer is not adjusted. The slicer uses sharp blades to create clean edges. Dull blades tear cells and create ragged surfaces that absorb more oil and shed more fragments. Many chip lines also apply slice sorting. A screen separates small fragments and slivers from full slices. Slivers fry faster and become darker, so removing them improves color consistency. Some lines also classify slices by thickness using optical measurement and divert out-of-range slices. Keeping thickness narrow allows fryer time and temperature to remain stable. The potato feed to the slicer is stabilized by upstream size grading. Potatoes arrive in bulk with variation in diameter and length. Large variations can cause feed surges and slicing inconsistency. A grader routes potatoes to appropriate lanes or rejects extremes. Feed hoppers and belts deliver a steady flow to the slicer, so blade load remains consistent. Consistent blade load produces consistent thickness. Raw potato preparation begins at receiving. Potatoes enter water flumes that transport them while removing stones and heavy debris in trap sections. Spray washers remove soil that would dull blades and discolor oil. Peeling is used on many lines. Abrasive peelers remove skin by rubbing against carborundum surfaces, while steam peeling can loosen skins quickly before mechanical removal. Peeling choice depends on product style. For classic thin chips, peeled potatoes provide uniform color and reduce dark spots. After peeling, potatoes are rinsed to remove peel fragments and then inspected by optical sorters that remove rotten spots and green areas that would fry dark and taste bitter. Temperature control begins early because potato temperature affects slicing and frying. Cold potatoes slice more cleanly and release less surface starch, but very cold potatoes can have higher reducing sugar levels from cold storage, which increases browning. The plant manages potato storage and tempering so raw potatoes arrive at a temperature that supports both slice quality and target color. Reducing sugar content is managed through raw material selection and sometimes through brief conditioning treatments. Potatoes with high reducing sugars brown too fast and produce dark chips. Wash and blanch steps are more common for fries than for chips, but some chip lines manage sugar through storage control and by blending lots. The goal is consistent color without relying on heavy downstream correction. After slicing and washing, the system focuses on gentle transport. Slices move through flumes and onto dewatering belts. The line avoids high drop heights because thin slices tear easily. Torn slices become fines and increase oil degradation in the fryer. Gentle transport reduces breakage and improves yield. The transition into the fryer is designed to avoid clumping. Slices are spread into a uniform layer before entering oil. Spreading can be done with distribution belts or vibratory feeders. A uniform entry layer ensures every slice sees similar oil contact and similar dwell time, producing uniform moisture removal and color. After frying, chips pass through a color sorting stage on many lines. Cameras measure chip color and eject overly dark chips with air jets. This stage compensates for occasional raw potato variability and fryer transient conditions. Sorting reduces the incidence of bitter dark chips in the bag and improves visual uniformity. Hershey's milk chocolate is produced by taking dry solids that would feel gritty on the tongue, suspending them in cocoa butter and milk fat, then forcing that suspension through particle reduction, moisture stripping, and crystal control until it can be poured into molds and set into stable bars. Chocolate begins as a set of dry streams that must be kept dry. Sugar is received as granulated crystals and screened to remove clumps that resist grinding. Milk solids arrive as powders and are sieved because compacted lumps do not disperse evenly and later create specks. Cocoa solids arrive as cocoa liquor, cocoa butter, and sometimes cocoa powder, depending on the formula and plant layout. Cocoa butter is melted and filtered. Cocoa liquor is held warm, so it remains pumpable and is filtered to remove unmelted fragments. Water is kept out of all these streams because even small moisture content causes chocolate to thicken sharply. The first assembly step is a premix that creates a uniform paste for refining. Melted cocoa butter and cocoa liquor create the continuous fat phase in a mixer. Sugar and milk powders are introduced gradually so they become wetted rather than forming dry islands. The mixer uses high torque and wall scraping because the mass is thick before refining. The goal is not smoothness yet, but even distribution of solids so downstream mills see a consistent feed. Particle size reduction is then applied. Refining is performed with roll refiners or equivalent milling equipment that squeezes the paste through narrowing gaps. Each pass breaks sugar crystals and reduces the size of milk and cocoa particles. The target is a particle size below the tactile threshold on the tongue. When the chocolate reaches this range, its texture becomes smooth rather than sandy. The output of roll refining often emerges as thin flakes because the refined mass forms a film on the final roll and breaks off. Those flakes behave dry because they have huge surface area and not enough free fat coating at their surfaces. They also hold trace moisture and trapped air. If left untreated, they will make the chocolate thick and harsh. Conching is the step that fixes both flavor and flow. Conching combines heat, time, and mechanical work to coat particles fully with fat and drive off moisture. The refined flakes enter a conch where paddles knead the mass. Heat keeps cocoa butter fluid so it can spread across particle surfaces. Mechanical shear breaks down any remaining agglomerates and distributes fat uniformly. Airflow through the conch carries away moisture and volatile compounds. Moisture removal is critical because water causes particles to cling together and raises viscosity. During early conching, the chocolate may appear pasty and resistant. As conching continues, friction drops and the mass becomes more fluid and glossy. This change is the result of improved fat wetting and lower moisture. The conch is controlled to reach a defined viscosity and yield stress that matches the needs of molding equipment. Too thick, and the depositor will underfill corners and create air pockets. Too thin, and the bar edges will become heavy and the surface will be more prone to flow marks. Emulsifiers are typically added late in conching to fine-tune flow. Lecithin reduces yield stress by improving particle wetting. Additional emulsifiers can be used to further reduce viscosity at the same fat level. These additions are dosed precisely because small changes have large effects on how the chocolate runs through pumps, valves, and deposit heads. After conching, the chocolate is transferred to holding tanks with gentle agitation. Agitation prevents separation and keeps the suspension uniform. Temperature is held stable because viscosity is temperature sensitive. The chocolate is filtered again before tempering to remove any remaining lumps that could block depositor nozzles or cause surface defects in molded bars. Tempering is where the bar's final structure is engineered. Cocoa butter can crystallize in multiple forms, but only one dominant form produces the desired gloss, snap, and contraction for mold release. Tempering machines first heat the chocolate to erase existing crystal memory. They then cool the chocolate under agitation to nucleate crystals. Finally, they reheat slightly to melt unstable crystals while leaving stable seeds. The result is a chocolate that remains fluid at working temperature while carrying a controlled population of stable seed crystals. The tempered chocolate feeds molding lines. Molds are cleaned and conditioned so their surfaces are dry and at a controlled temperature. A mold that is too cold can cause premature setting and poor surface finish. A mold that is too warm can slow setting and increase smear risk. Deposit heads meter a precise mass into each cavity. Mass control is essential because bar weight is regulated and because cooling time depends on thickness. After deposit, molds pass over vibrating tables. Vibration removes trapped air bubbles and levels the surface. It also helps the chocolate flow into fine corners and embossed details. Vibration intensity is controlled because excessive vibration can create thin edges and heavy centers. The filled molds then enter a cooling tunnel. Cooling is staged to set the chocolate without creating stress or bloom. The first zone sets the surface quickly to protect shape. Later, zones cool more gradually so the interior solidifies while stable crystals grow. The chocolate contracts slightly as it cools, which creates a gap between the bar and mold wall and enables release. Cooling that is too fast can produce internal stress cracks or a dull surface. Cooling that is too slow reduces throughput and can leave soft surfaces that pick up marks. When the bars reach the release temperature, the molds are inverted or flexed and the bars drop out. Release performance is a sensitive indicator of correct temper. If temper is weak, bars cling to molds and show smeared surfaces. If temper is strong and cooling is correct, release is clean and the surface is glossy. After demolding, bars are conveyed gently to avoid scuffing. Inspection checks can identify broken corners, surface voids, and weight deviations. Bars that fail are diverted to rework streams. Reworked chocolate is remelted and returned upstream because it cannot be reintroduced directly into tempered chocolate without resetting its crystal state. Packaging begins once bars are fully set. Wrapping material is folded around each bar and sealed. Seal temperature and dwell time are controlled so film closes without heating the bar enough to soften the surface. Wrap tension is controlled to avoid imprinting. Codes are printed for traceability and packs are inspected for seal integrity. Bars are then cartoned or case packed for distribution. Maltesers are manufactured by first creating a rigid, hollow, malted honeycomb core that is mostly air, then sealing that fragile core with a thin chocolate layer, then finishing it with a stable outer chocolate coat before cooling, screening, and packaging. Everything starts with the center, because the honeycomb is not molded like a solid candy. It is created by generating gas inside a very hot sugar melt and then freezing that gas structure before it collapses. The center, therefore, needs a syrup that can foam explosively, set fast, and remain dry enough to stay crisp inside chocolate. Sugar is staged as a dry crystal feed and screened to remove clumps that can seed crystallization. Glucose syrup is held warm so it pumps smoothly and helps prevent uncontrolled graining. Malt extract or malt syrup is prepared as its own stream because it brings both flavor and solids and influences viscosity. Water is filtered and tempered because it affects dissolution and cook consistency. A small amount of fat may be included in some systems to control bubble wall brittleness, but the dominant structure comes from sugar glass. The syrup is cooked to a very high solids level. Sugar, water, glucose syrup, and malt components are dissolved and then heated rapidly in a cooker. The cook endpoint is chosen to make a glass that is brittle and sets quickly. If the syrup is too wet, the foam collapses before setting and the honeycomb becomes dense. If too dry, the melt becomes too viscous to expand evenly and can trap large irregular voids rather than a fine network. As the syrup reaches endpoint, it is transferred quickly to a mixing and aeration stage. This stage is designed to incorporate a gas-generating agent at the last moment. The syrup temperature is still high enough to keep viscosity low, but it must not be so high that the agent decomposes too early in the pipework. The gas-generating agent is introduced in a controlled dose, and the syrup is mixed just enough to distribute it without deflating the forming foam. The moment the agent reacts, gas expands through the melt and inflates it into a foam. Expansion is rapid, so the process immediately directs the foaming mass into a casting system. The foam is deposited into trays or onto a belt in a thick slab. The slab rises as gas expands, then begins to set as the melt cools and transitions into a glass. Cooling is engineered to lock the foam architecture. The outer surface must set quickly so the slab holds its height, while the interior must cool enough that bubble walls become rigid. Airflow and plate cooling are used to pull heat out without introducing humidity. Humidity control matters because a fresh honeycomb surface is hygroscopic and will become sticky if it absorbs moisture. Once the honeycomb slab reaches a cuttable brittleness, it is broken down into cores. This is not a clean slicing operation because honeycomb fractures along cell walls. The slab enters a breaker that applies controlled compression to crack it into chunks. The goal is to generate pieces that will later be rounded and sized rather than leaving long jagged shards. The breaker is tuned to minimize powder because honeycomb dust contaminates chocolate and dulls coatings. After primary break, the pieces are sized and shaped. Screening separates oversized chunks, target pieces, and fines. Oversized chunks are returned to the breaker. Fines are removed because they create dust and can clump. The target fraction moves to rounding drums that tumble pieces gently and knock off sharp spikes. Rounding improves coating coverage and reduces punctures that can rupture the chocolate film later. The honeycomb cores are extremely fragile, so conveying is designed with low drops and soft transitions. Vibrations are minimized because they generate dust and fracture. The cores are also conditioned in dry air. Conditioning equalizes temperature and reduces surface tack. It also stabilizes moisture so the cores do not soften before chocolate sealing. Before full coating, the honeycomb is usually sealed. Sealing is a thin chocolate or compound layer that penetrates slightly into surface pores and blocks moisture transfer. Without sealing, the honeycomb would absorb moisture from the chocolate environment and later from the package headspace, losing crispness. Sealing, therefore, acts as a barrier layer and a structural reinforcement. Sealing chocolate is prepared and held at a viscosity that can wet porous surfaces without flooding them. If real chocolate is used, Tempering is applied so the seal sets quickly and remains stable. If a compound coating is used, temperature control sets viscosity and set speed. The cores enter a pre-coat stage where they are tumbled while a fine chocolate spray is applied. The spray is light and repeated in several passes because a heavy single application would collapse the honeycomb edges and create thick, uneven spots. After sealing, the cores pass through a short cooling tunnel to set the thin layer. Cooling is tuned to harden the surface while keeping the core dry. Once sealed, the cores can survive the more aggressive motion of full enrobing or panning. The final chocolate coating is applied either by enrobing with a curtain or by panning in rotating drums, depending on the line design. For Malteser's style spheres, panning is often used because it builds an even coat around irregular cores. The sealed centers are loaded into rotating drums, and a measured amount of chocolate is applied in stages. Each stage adds a thin film, and then cooling air sets it before the next film is applied. This staged build prevents the weight of wet chocolate from deforming the fragile centers and prevents pieces from sticking together. Chocolate viscosity and temperature are controlled tightly during coating. Too warm and chocolate becomes thin, runs and pools, leaving uneven thickness. Too cool and chocolate thickens, builds rough surfaces, and fails to flow into small contours. If real chocolate is used, temper control is critical because the coating must set with stable crystals to resist bloom and to provide a clean snap. The coating system therefore monitors temperature and flow resistance and adjusts cooling and heating to keep chocolate in the working range. As coating thickness builds, the process focuses on surface smoothness. Early layers are allowed to penetrate and lock onto the sealed surface. Later layers are applied in thinner films with longer setting time to reduce texture. Drum speed is tuned so pieces roll rather than slide. Rolling distributes chocolate evenly and prevents flats. Sliding creates thin spots and scuffs. Once the coating reaches target thickness, pieces enter a final cooling tunnel. Cooling is staged to avoid stress cracks. The outer surface is set first to protect shape. The interior of the chocolate coat is then cooled gradually so crystals stabilize. Stable cooling also prevents condensation. Condensation causes sugar bloom and surface haze, which is especially visible on smooth chocolate spheres. After cooling, pieces are screened to remove doubles and broken cores. Doubles occur when two pieces stick during a wet stage. Broken pieces shed honeycomb dust and compromise appearance. Screening uses mesh decks sized to the product diameter band. Off-size pieces are diverted. Quality checks focus on core crispness and coating integrity. Crispness is influenced by honeycomb moisture and by seal coverage. Coating integrity is influenced by chocolate temper and cooling. Weight checks confirm coat thickness and core mass remain stable. Visual inspection can detect flat spots and scuffs that indicate coating issues. Packaging begins only after pieces are fully set and at a stable temperature. Warm chocolate will mark and also may release aroma components differently. The pieces are conveyed gently into multi-head weighers. Flow is aided by the spherical shape, but fines can still cause bridging, so dust control remains important. The weigher portions target weights by combining small hopper dumps. Portions drop into bags formed on vertical form-fill seal machines or into cartons depending on format. Seal timing is tuned so chocolate pieces do not lodge in the seal area. Seal integrity matters because moisture ingress will soften honeycomb through the chocolate over time. Packaging films are selected for moisture barrier performance because protecting core crispness is the main shelf life requirement. Case packing and palletizing are designed to limit crushing and temperature swings. Excess vibration creates scuffs. Temperature spikes can soften chocolate and accelerate bloom risk. Stable storage conditions help maintain coating gloss and keep the honeycomb core dry and crisp. The crunch of a Smarties shell is not an accident. It is built one microlayer at a time until a measured thickness of crystalline sugar surrounds a chocolate core and behaves like a small engineered capsule. The process begins by defining the target finished diameter and shell thickness, because those two numbers determine everything else. Once the shell target is set, the center must be manufactured to a diameter band that leaves enough room for the shell to grow without producing oversized pieces. That means the chocolate core is treated as a precision pellet rather than a simple molded chocolate. Chocolate preparation starts with creating a stable suspension of solids in fat. Cocoa components, sugar, and milk solids are blended so powders are evenly distributed. Refining reduces particle size so the chocolate is smooth and so the core surface is dense rather than crumbly. Conching follows to complete fat wetting and remove residual moisture, because moisture would later cause texture defects in the shell build. The chocolate is then tempered so cocoa butter forms stable crystals. Temper stability matters here because the core will be tumbled for long periods in rotating pans, and a poorly crystallized core would soften and flatten under repeated impacts. Core shaping is done to achieve a lens profile that rolls predictably. The chocolate is metered in small doses, either into shallow cavities or onto a cooled surface where it can be shaped. Metering controls mass tightly so core weight distribution stays narrow. Shaping controls curvature so the piece does not develop a flat face. Flat faces roll differently and receive shell build unevenly. After shaping, cores are cooled in staged tunnels so they harden without cracking and so their surface remains dry and non-tacky. Before shell building, cores are conditioned. Conditioning brings the cores to a temperature where they are hard enough to resist dents but not so cold that their rims chip and create sharp edges. Rim chipping is a problem because chips become weak points where shells later crack. Conditioning also prevents condensation because any surface moisture would dissolve the first sugar layers and create rough, orange peel textures. Shell building is carried out in rotating pans or perforated coating drums. The cores enter as a rolling bed that must remain in a consistent cascade. Drum fill level and rotational speed are set to create rolling contact rather than sliding. Rolling ensures all surfaces are exposed evenly to syrup and air. Sliding causes flat spots and uneven thickness. The mechanical motion is therefore treated as a controlled input in the same way as syrup concentration. The first shell layers are designed as a bonding bridge. A light syrup is atomized into very fine droplets and sprayed in short pulses. Droplet size is kept small so it spreads thinly and does not pool. Immediately after each pulse, drying air flows through the bed and removes water so a crystalline film forms at the surface. This early stage must be fast setting to prevent pieces from sticking together and forming twins. It must also be gentle enough not to soften the chocolate core. Once adhesion is established, the process switches to thickness build cycles. A higher solid syrup is applied, then fine sugar is introduced as a dust. The dust absorbs moisture from the syrup film and accelerates crystallization. Drying air then removes remaining water and strengthens the new layer. This spray dust dry sequence is repeated many times. Each individual layer is thin because thin layers crystallize more evenly and reduce internal stress. Thick layers dry unevenly and create trapped moisture pockets that later pit or crack. Drying conditions are tuned continuously. Air temperature must be high enough to evaporate water efficiently, but not so high that it warms the chocolate core and risks deformation. Air humidity must remain low enough to pull moisture out, but not so low that the surface hardens instantly and traps water inside the shell. The process balances these factors, so crystallization progresses through the layer thickness, rather than forming a hardened skin on top of a damp interior. As the shell thickens, the sound and motion of the bed change. Pieces become harder and collision noise becomes sharper. The process compensates by adjusting drum speed slightly to maintain rolling without excessive impact. Too much impact at this stage chips edges and creates exposed shell layers. Too little impact produces irregular shapes and non-uniform thickness. Near the target thickness, the focus shifts to smoothing. Dust addition is reduced because dust tends to leave a rough micro texture. Instead, thinner syrup films are sprayed and given longer drying time. Thin films flow into micro valleys and reduce ridges created during bulk build. This is also where roundness improves, because mild abrasion during tumbling knocks down high points and helps the shell approach an even curvature. Color application is treated as a separate operation, layered on top of the structural shell. Color solutions are prepared to precise concentration and filtered to remove undissolved particles that could create specks. Color is applied in multiple light coats rather than one heavy coat. A light coat wets the surface uniformly and dries quickly without pooling. Pooling creates blotches and uneven shade. Between coats, drying air sets the film completely so the next coat does not dissolve the previous one. Color is typically introduced when the shell has reached most of its thickness but still has enough surface receptivity for good adhesion. Introducing color too early risks burying pigment under later clear layers and muting shade. Introducing color too late risks weak adhesion and rub-off because the surface can be too hard and slick. The process therefore schedules color passes within a window where the surface still accepts thin films but the shell is strong enough to tolerate extra handling. Because multiple colors are produced, color runs are separated to prevent cross tint. Spray lines are flushed between colors and pans are cleaned so residue does not contaminate the next batch. Shade is checked with optical measurement and adjusted by adding additional light passes or altering concentration within a narrow range. Uniform shade depends on maintaining consistent bed motion and consistent droplet size because any change in wetting pattern shows as streaks. After color, a protective finish layer is applied. This can be a clear syrup coat that locks pigment and reduces rub-off. The clear coat is applied sparingly to avoid creating a sticky surface. It is followed by extended drying so moisture reaches a stable endpoint. Moisture endpoint determines both crunch and handling. Too much moisture makes shells tacky and prone to scuffing. Too little moisture makes shells brittle and prone to chipping during conveying. Moisture equalization follows drying. Even when the surface feels dry, the inner shell can retain slightly different moisture. Equalization holds the candies in controlled air so gradients flatten. This reduces internal stress that can cause fine hairline cracks and improves shelf stability. Polishing is the final surface engineering step. A very small amount of polishing agent is misted into a polishing pan while pieces tumble gently. The film spreads across the shell's surface and fills micro pores, increasing gloss and reducing friction. Reduced friction improves flow through hoppers and reduces scuffing in packaging. Polishing is controlled carefully because excess polish can feel waxy and can reduce the crisp sensory perception of the shell. If a printed mark is used, it is applied after the surface is smooth and dry. Printing uses edible ink transferred by a pad system. Pieces are fed and oriented so a stable face is presented. The pad picks up ink from an etched plate and stamps it onto the shell. Ink viscosity and pad pressure are tuned so the mark is crisp without smearing. A short drying stage sets the ink before pieces are mixed and conveyed. Sorting and sizing occur before packaging. Screens remove fines and broken fragments. Optical sorting removes twins, chipped shells, and off-color pieces. Size classification removes pieces outside the diameter band because off-size pieces disrupt appearance and affect weigher accuracy. Sorting also protects packaging because irregular pieces can bridge or jam. Conveying is designed to minimize impact. Drop heights are kept low and chutes are smooth and curved. Hoppers are steep and low friction to maintain flow without heavy vibration. Excess vibration increases abrasion and creates dust that dulls gloss and contaminates seals. Packaging starts with portioning. Multi-head weighers distribute candies into multiple hoppers and select combinations that meet the target weight precisely. Accurate portioning depends on consistent piece size and free flow. The portion drops into a bag formed by a vertical form-fill seal machine or into a carton fill funnel depending on format. Seals are made while keeping candies away from the seal zone because trapped pieces or sugar dust can create leaks.